You can unmute. Okay, you unmuted, yeah.
Yes. Our first speaker today is Jorge Lopez. He is the president and founder of LDC Energy Consulting, LLC, and president and co-founder of Resin Tech, LLC. He provides technologies for water management for the oil and gas industry, as well as consulting services on perforating strategies to reduce costs, environmental impact, and preparedness for transition to lower carbon energy sources. Jorge worked 33 years for Schlumberger with several positions in R&D and operations, including Director of Technology at Schlumberger Mexico and Central America, Director of Heavy Oil Center of Excellence in Venezuela, Manager of Perforating R&D and Manufacturing Group at Schlumberger Reservoir Completion Center worldwide, Heavy Oil Theme Manager, Worldwide Sand Manager, Solutions Manager, Cased Hole Business Development Manager of North and South America. Prior to Schlumberger, Jorge was an assistant professor of physics and thermodynamics at Universidad Iberoamericana in Mexico City, holder of several patents on perforating downhole tools and completion techniques. Mr. López-de-Cárdenas has a BS, a degree in mechanical engineering, and a master's of science in mechanical engineering from the University of Houston. And with that, I'll let Mr. Jorge present his topic.
Good morning, everybody. Thank you, Jeff, for the introduction. It is a real pleasure to be able to contribute with this brief seminar to the Pay Forward initiative. Let me share my screen so that you can. To be allowed to share my screen.
Jorge, are you having some problems?
Yes, I am disabled. I cannot share my screen. I get an error message saying that I'm the host disabled participant from screen.
Salim, can you make sure that we set Jorge back as a co-host? I guess a setting got mixed up, reset when we came back from the break.
Is that? Okay, just a minute. I'm not even able to get out to my. So what is the problem here? I can't even go to the participant list.
What do you see?
I just see Jorge alone because I spotlighted him.
Let me.
The participant list, can you find Jorge and make him a co-host?
Yeah.
Come on.
Okay. Try now, Jorge.
Yeah, that should work. Carlos, thanks for your help. Sorry about the trouble.
No problem. I think now I have control. So let me. Okay. Can you see my first slide?
Yes.
Great. So today I will be talking about perforating, which is a critical but often overlooked operation of the completion programs of a well. I will discuss the role of perforating for optimal sand phase completions, particularly for wells requiring hydraulic fracturing. So let me go here to advance. Good. So I divide with an overview of the main reservoir types and the role of perforating for each one of them. Then I'll go over some of the key characteristics of the typical perforating systems and the shape charges in use today. And then I'll talk about the main topic of today's presentation, which is perforating for hydraulic fracturing. I will cover the cases of vertical wells, horizontal wells, multi-stage completions, and I'll make some comments about limited entry. Finally, I'll present some recommendations perforating gun system. I would like to warn everybody that in about 45-minute presentation, I will only be able to go over the generalities of these topics. But at the end of the presentation, I have included a list of references for those of you that might want or might be interested in learning more about the specifics of these topics. And of course, we also have a Q&A session at the end. So in planning any completion program, the place to start, I always say, is with a good understanding of the reservoir, and recommend always to talk to the geologists, geophysicists, geomechanics experts. Learn about conditions, what is the pressure, temperature, all of the sample conditions, the rock, type of rock that you might have, the fluids, permeability, formation damage, and identify and understand which type of reservoir do you have. Now, for the planning of the perforating program, we think about three main reservoir types. The first one are reservoirs that have good permeability and are competent rock, that don't require any sand control completion or don't require any stimulation. We call those the natural completions. And in those cases, the objective is, let's see, the figure on the left is a top view of a well with a perforating gun inside of it and the shape charges, and you also show some of the perfs that it has created. And on the right is like a vertical cross-section of one of those perforations. So in this type of completions, the objective is to establish communication from the well to the virgin zone. Perforating, going beyond the damaged zone and reaching the area that has an original reservoir permeability, and bypassing or penetrating beyond the damaged zone that has a reduced permeability KP. So to do that, we do that with guns that have deep penetrating charges, where the main objective is to maximize the depth of penetration. The other type of reservoirs are the ones that are weak, that they may produce sand during the production of the life. And we have two main groups. You know, those that have rocks that are completely unconsolidated and definitely frac and pack. In those cases, the role of the perforating is to create a large hole in the casing that will allow me to place the gravel. And for that, we normally use big hole charges with a high shot density to maximize the area open to flow. There's also some other wells that might have the potential of producing sand, but they have a rock that it is more consolidated, but it is weak. So under any shear stresses, they might start producing some sand. In those cases, sometimes perforating could prevent or delay the need for a sand control completion. And we do that by using guns that produce smaller perforating holes, and we try to place them oriented in the areas that the perf tunnels are more to the horizontal stresses, looking areas of less contrast around the perforating guns. We also use high shot density guns to have a large area open to flow. The third type of reservoirs that I want to talk about are those on the opposite side, the ones that have very low permeability and they require stimulation. And so if they require hydraulic fracturing, we can think about cases like in plastic formations that you have a thick pay zone with a vertical well, or we can have also a well that might intersect several pay zones, and they might require multiple fractures in the same well. Or even the other extreme, like what we have today, very common today, especially in the US, with unconventionals, where we have a horizontal well that requires many fractures, and therefore many perforating intervals. They're going to be short perforating intervals, but several of them. But in all of these cases, the hole size is extremely important. Particularly, I'm going to emphasize that during my whole presentation, we require uniform hole size in all of the perfs. To satisfy the perforating requirements of the different completion times that we have mentioned, a large variety of perforating systems are available. They are available in lengths that can go from 1 foot to 20 foot, and in diameters as small as 1 11/16 of an inch to 7 inches. And they consist of explosive shaped charges. You can see them here on the left figure, that are typically mounted inside of a hollow gun carrier and mounted typically on a spiral pattern. And then they also use a detonating core that goes through the back of all of the charges. And then at the one end of that detonating core, a detonator that is used to initiate the detonation of the whole gun system. Now, with the advent of wells requiring many fractures with short perforating intervals, shorter and more efficient guns have been recently developed. Often they are called or referred to plug-and-play systems. These systems are more efficient because they can significantly reduce the operating time and the overall length of the tool string. The figures that I have here are just few examples of some of them, but there are many others. In fact, most service companies now, they have their own or are developing. Let's discuss the main factors related to perforating that could affect the productivity of a well. The figure here shows some of these parameters, but the ones that the perforating plan can affect are these four. The entrance hole diameter, which is this one, the penetration depth, the shot facing or face angle, and the shot density or the perforating spacing, and of course the perforating interval or the number of perforations that I have. So those are the four things that I can control. Now, let's talk about the heart and the source of energy of a perforating gun system, which is the shape charge. The shape charge is a technology that was taken from the military. It consists of a conformed shape explosive. You can see it here in the figure on gray. That it is formed by pressing it against a metallic case, which will be this brown case shown in here. And then it is covered with a conical liner that it is pressed against the explosive. So, in fact, I don't know if you can see my screen, but you know, this is a typical. It's a shape chart that has been cut just to show the liner, the explosive, and the case. And the conical liner is what will become the projectile that penetrates our targets. That is the casing, the cement, and the formation rock. Now, to illustrate how the liner becomes the projectile, I'll use some screenshots of a numerical simulation of the detonation of a shape charge. So in the figure, you can see in blue the case, in yellow the explosive, and in red the liner. Here on the back of the explosive, in this direction through the explosive, collapsing the liner and forming a jet. Here we see what happens with only 1 microsecond after the start of the detonation. It's something that happens extremely fast. Here, the pressures generated by the explosive are in the range of 1,000,000 psi. The liner has been collapsed, and it collapses with such a high energy that some of the particles get expelled to the front at a very high speed, forming a jet. Here we see the jet at about 11 microseconds, and here we can see the jet at about 60 microseconds. The speed of the tip of the jet is in the order of 7,000 meters per second. It's hypersonic. It's extremely fast. And the jet is going to continue expanding and traveling to penetrate through our targets. Something important to keep in mind is that the perforations that is going to create in the rock, they are not punched hole. So the material that it is missing in the void that the perf leaves, it hasn't been taken out like when we drill a well. It actually has been compacted and crushed and pushed to the sides. Something very important to keep in mind, especially when we deal with natural completions. Now let's talk about the type of explosives that are used in the perforating guns. There are three main types of explosives that normally are used in the oil and gas industry: RDX, HMX, and HNS. And the graph that I'm presenting here, it shows the temperature rating of these three explosives as a function of time. So, for example, for a typical wireline operation where the guns are going to be at the bottom of the well, let's say for typically less than an hour, the ratings would be for RDX 340, you can see it over here, for HMX 400 degrees Fahrenheit, and for HNS 500 degrees Fahrenheit. Fracturing, RDX is normally the one that satisfies the requirements. But if, for example, we were dealing with a TCP operation or a operation in a horizontal well with tractors that the guns might be in the well, let's say, for up to 10 hours, and the temperature would be 300 degrees, then we can see that at 10 hours and 300 degrees, RDX would not be enough. We will have to use HMX. Of course, the cost of these explosives, they're higher as well. So, but that's something that we will have to do. And checking the expected temperature and time conditions of the operation is very important for selecting the correct type of explosive. Now let's talk about the different charge types that we have available. They can broadly be divided into three main groups. Charges with deep penetration, with the big hole charges for sand control, or charges that sometimes they are referred to good hole or adequate hole for hydraulic fracturing. And deep penetrating charges, they are optimized to have the deepest penetration into the rock. As an example, and just for comparison purposes, if we look at the API, which is in a concrete target, they can vary depending on the size of the gun and the charges. They can go from 11 inches to up to 65 inches of penetration in the concrete block. And the hole size will be from, around 0.2 to half an inch. In comparison, the big hole charges used for sand control will create a bigger hole in the casing that could go from 0.4 to 1 inch. Penetration is not so important in these cases. I didn't put over here, but it is very much compromised. The penetrations of these charges could be in the range of only, 6 to 8 inches or 10 inches. Is much less than the other ones because the objective is to make a big hole. Then somewhere in between are the charges for hydraulic fracturing, where the entrance hole diameter, typically they go from about 0.25 to from a quarter of an inch to about half an inch. And then the liners that are used, which is our penetrator into the rocks, could be of two types. One that are formed from powder metal, normally is a mixture of tungsten, copper, lead, and sometimes they put salt and pepper. The manufacturers, I'm kidding. They have their own recipes, which are just proprietary information, but it is basically a powder, a mixture of powders that they press and they form the liner with that. And those are typically used for deep penetrating charges and sometimes for the good hole charges. The big hole charges are typically made with solid metal liners, which are made of punching a sheet of copper or copper alloys. Now, in more recent years, you will hear, especially a lot now in in hydraulic fracturing of a new type of charges called uniform hole or equal hole charges. They are basically good hole charges for hydraulic fracturing that the liner has been optimized to make a more uniform hole size independent of the water that they might have to travel when they travel from the gun to the casing. So they are called uniform hole charges, and they are typically made from powder metal liners. Now, okay, next let's review in more detail the role of the perforating in hydraulic fracturing, which is the main topic. And let's start by remembering how a fracture is formed. Let's start with the case of a vertical well. So the objective, the figure shows, a thick paison and a perforating gun with a good perforating interval. The objective will be to put pressure around the wellbore. The figure also shows the in situ stresses. We have the overburden stress, the maximum horizontal stress, and the minimum horizontal stress, sigma 1, sigma 2, and sigma 3 typically. Normally the overburden is the largest one, typical. Not always, but typically. So to create a fracture, what we need to do is to exert a pressure in the wellbore that will be higher than the minimum horizontal stress. And what will happen is that pressure will push the rock into this direction and into this direction, into the direction of the minimum horizontal stresses, because it's the weaker of all of them. And that will create a fracture that will propagate in the direction of the maximum stresses. So we have a fracture that propagates perpendicular to the minimum stresses. This is what we call the perforation fracture plane. So what the role of the perforating is to establish that communication that will allow that communication between the well and the wellbore that will allow me to apply the pressure that is needed. And also the objective is to facilitate the pumping of the fracking fluids and the proppant that I'm going to do that. And we want to do all of that minimizing the surface pressure. And some of the issues that we need to address during that operation is reducing the breakdown pressure, controlling the perforation friction, reducing tortuosity, avoiding proppant bridging, which could create premature screen-outs, and avoiding in vertical wells multiple fractures, which could be an issue. Let me explain these issues and what perforating can do to affect them. So I listed here, the bad actors in red at the bottom of this slide, and at the bottom in blue, the things that I have to control those. And let's look at an example of a well that has the perforations aligned perpendicular to the minimum horizontal stress. So they will be aligned with the perforation fracture plane. When I start applying pressure on it, the rock is going to move in the direction of the minimum stress, and I'm going to create a fracture. And in this case, the perforating holes are going to be perfectly aligned with the fracture that I have created. This is an ideal case. This is an ideal situation. But what would happen if the minimum horizontal stress is not perpendicular to the perforations? Now, the rock is still going to now move in the direction of the minimum horizontal stress. So when I apply pressure, first of all, my breakdown pressure might be higher. Typically, it's going to be higher than if they were perfectly oriented, like in the case before. And when I start applying the pressure, eventually the rock is going to separate and move in the direction of the perforation fracture plane, pushing the rock into the direction of the minimum horizontal stress and creating the fractures. But those fractures now, they may not be aligned with the perforations. So when I start producing the well, the fluids, they need to follow a trajectory that has more tortuosity and therefore more pressure drop and losses during the production of the well or during the pumping of the fracture. The other thing that could happen also is that when the fracture was created, there could be a competing multiple fracture that might start from the base of the perforation tunnel, which also is a not desirable condition. So a lot of tests has been done in big blocks, stress frame and stress blocks, and in the field. And I'm not have time to go into the details, but the conclusion has been reached that if you shoot 60 or 120 degrees are very good options to minimize these effects. Of course, the best one will be 180 degrees if you can orient the guns, which it is possible. The technology exists for doing that. It is just more expensive to do that, and therefore is not done so frequently. But 60 and 120 degrees are very common for hydraulic fracturing, and this is the reason why. By the way, a lot of guns for sand control, they have a 45-degree facing. They are not recommended for hydraulic fracturing. 60 or 120 are better. The other problem that I want to address with the hole size is the potential breaching of the sand or the of the proppant when it is being pumped. And let me go to the next slide. So to prevent that one, the recommendation is to have a hole size that will be at least 6 times the diameter of the proppant. This is a table from the Schlumberger handbook that shows the gravel size distribution. So for example, if we were dealing with a well that is going to require a 2040 gravel proppant, we can see here from the chart that, let me read it, the sizes of the could be between 0.033 and as small as 0.017. So we need 6 times the size of the proppant. The one that we need to take is to take the larger size, the 0.033. So if it is a 24, I take 0.033 times 6, that will give me about a 0.2 of an inch. That would be the minimum hole size that is recommended for a 2040 to prevent the potential of having breaching. Now, I will mention that it's also very important to have uniform hole size. And to understand the reason why, let's take a look at the equation that gives me the pressure drop of a fluid when it is pumped through a hole. And in our case, that one is called the perforating friction or perforation friction. And it is given by this equation. You can see that it is a function of the flow rate. It is a function of the flow rate. It is a function of the specific gravity, the casing entrance hole diameter, the discharge coefficient, and the number of perforations that we have. That's what's going to give me what is called the perforation friction. But notice that the diameter of the hole in the casing is the variable with the most weight in this equation, is to the 4th. So small changes in here will have a fairly large effect on the perforation friction. And that is important because, as I mentioned before, when we shoot a gun with a facing, and this is a schematic showing a top view of the gun with the shape charges and the casing, you can see that the charges that are going to be on the low side, they have very water clearance to travel through. However, the ones at 120 degrees, 180 or 240, they have much water to travel through, and that may affect the size of the hole that they're going to create in the casing. So to visualize that one, we can look at the following slide. Here, we can see the typical holes that you will obtain with the standard big hole charges, or good hole charges. And you can see that the hole sizes for the 0, the 60, and the 300 degrees are fairly big and uniform. But if we look at the holes at 120 degrees, 180, and 240, you can see how much smaller they are. And if they happen to be, for example, half the diameter of this other one, when I try to pump a fluid through these holes than from that, 16 times. So when I try to inject a fluid, most, if not all of the fluid is going to go through the big perforations and nothing or almost nothing through the small one. Something very important to consider in our designs. So To solve that problem, the industry in recent years have come with the designs of the more uniform hole charges that can have a more consistent hole size, independent up to a certain point of the water clearance that they typically have to travel. So, and that shows an example of the holes made with a uniform hole charge versus a conventional charge. Now, another thing to keep in mind, and that is interesting to note, is that the casing entrance hole might get enlarged or elongated during the pumping of the slurry, and that is a result of the erosion. Pictures that were taken with a downhole camera in a recent, and they were published in a recent SPE paper, that the one that is listed over there. So the figures on the left show how the proppant eroded the original hole, and the hole now has been elongated. You can see it over here. The pictures on the right compares the erosion of this particular perforation with that of another hole that apparently the flow didn't go through that. And the most likely reason why this perf did not take flow is because originally, so the fluid went through that one. Now, the other thing to notice is that the discharge coefficient that we saw in here is also going to be changing over time, because the shape and the size of the hole is changing. So it's something that is not static, and it's something that it is going to be important for limited entry, the planning of limited entry jobs. But so in conclusions, the recommendation for perforating for fracturing in vertical wells are make sure that the casing entrance hole diameter that you're going to create has a diameter of at least 6 times the proppant. Make sure that you're going to have uniform hole sizes in all of the faces of your perforations. If you can, 180-degree face oriented with the preferential fracture plane would be the ideal, but if it is too expensive or cannot orient it, or you don't know if the preferential fracture plane is unknown, then 120 or 60-degree facing are the ones that are the most recommended for this type of wells. Now, let's look at the case of a horizontal well. In a horizontal well, typically it is drilled in the direction of the minimum horizontal stresses. So in this type of cases, I don't need a large perforating interval. I just need something very short that will allow me to communicate my fluids around the well and to create the pressure that is going to push the rock apart in the direction of the minimum horizontal stresses and create the fracture. And because I'm going to create multiple of those, the only thing that I need is short perforating intervals in each one of the zones that I want to create a fracture like this one. So the recommendations for horizontal wells is, the same as the vertical ones, except that we recommend to use shorter perforating intervals, and the design, because we're going to need multiple guns in the same stream, in the same string, efficiency and reliability are very important in this type of wells. And here you can see an example of a long horizontal well using unconventional reservoir. The number of stages have increased over the years. They started with only 10 stages at the beginning, and then they went to 15, 20, 40. Now I have heard about going up to 60 stages, and the number of clusters that you put per stage has also increased over the years. It started with 2 to 4. Now having around 15 is fairly common, or 20, clusters of perforations per each stage. So with with that in mind, oops, just a second. With that in mind, let's look at the other challenges that these type of wells might present that have so many multiple fractures. Here the figure shows the fractures in the ideal case, where all of them look very homogeneous and they have the same length. But if you think about it, I mean, the ones that are farther away, they're going to have more pressure drop just because of the pressure drop of the liquids traveling through the casing. And also the rock has some inhomogeneities. And if we look at the real case of how the fractures might look in a stage, it might look something like that. And this is a picture taken from a numerical simulation, and it just shows the geometry of the fractures, and you can see that they will be quite different. So to address this issue, that's where limited entry comes into place, and that is something that is very important to take into consideration. And limited entry is actually not a new technology, it's fairly old, but I understand that our next speaker, Bob Barbe, will talk more about it, and also about a new version of it that is called extreme limited entry. But the general idea is to control the perforation friction to allow the diversion of the flow to the other perf stages, perf clusters that require more flow. And the way that you do that is by controlling the diameter and the number of perforations using this equation. That's the whole idea between, or the basic idea of limited entry. So let me now talk a little bit about the recommendations for the selection criteria. Of course, the most important criteria in selecting the perforating system that you want to use is use the most economical system that satisfies the requirements. But I want to share with you some other considerations that, although might be common sense, sometimes they are not so common or overlooked, and I believe that they're really worth mentioning. Choose trusted people and companies when selecting your systems. Always keep the reservoir in mind. Review the safety and the reliability of the whole system. Verify what is going to be your expected bottom hole conditions, what is going to be your bottom hole pressure, the maximum temperature that you might experience, the time that you might experience, the maximum time that the GAN systems might experience, and choose the explosives accordingly for all of the components that use explosives, the detonators, the detonating core, and the charges. I've seen some cases where they realize that they need to use HMX, but RDX is not enough, and they change the charges, but they forget about the detonating core, for example, and they keep using the RDX in the core when it should have also be changed. So make sure that you're consistent and you look at all of the components. If you're going to have multiple guns in the string and there's going to be the need of using selective switches, then ask about the type of them and the reliability. What is the reliability to be expected? And when possible, try to use the largest possible gun size for the casing size that you are dealing with. And finally, check and verify the expected performance of the system that you're going to have. And to finalize, let me give you some comments about how to verify the expected performance of the systems. There's three ways to check the expected performance of a perforating systems are, one, looking at the API 19B data, if it is available, doing some modeling, or conducting representative tests. For the case of hydraulic fracturing, to me, doing the test is the best option, and let me explain why. The disadvantage of the API data are that, number one, API tests are quite expensive. And the target is a big block of concrete that may not be representative of the actual penetration in the rock. Now, for hydraulic fracturing, we don't care about the penetration. We care about the hole size, so we can say, well, I can use the hole size of the API data. That is correct. However, be aware that the API tests are conducted in L80 casing only. That's the specification. And the most common casing grade used for hydraulic fracturing jobs in the US is P110. So then the data that is reported for L80 is not applicable for P110. And the entrance hole is affected by the grade of the casing, you know, the strength of the casing. By the way, by the grade, that is the strength of the casing. So in an L80 casing, we should expect to have a larger hole size than in a P110 casing. Now, modeling can be very good, and it is normally very good at predicting the actual penetration in some types of rock. But to predict really the changes in the hole diameters, they are not so good. They give you a good indication, but for our purposes, to me, that's not the best. The best is actually to do some tests. And the testing, on the other hand, if conducted properly, as shown in this figure, will give you the best data of what we might expect. But the gun was positioned all the way against the side of the casing, reproducing the downhole conditions, and the annulus between the gun and the casing is filled with the casing, and then it is shot. Sometimes it is shot with concrete behind the casing or behind the casing. Either way, for determining the hole size is fairly good, and having concrete behind doesn't affect much the hole size, so it could be done either way. But using the same type of casing that you're going to have in your well is very important, and make sure that the gun is positioned properly. So to recap what we have discussed today, let me say that and finalize by saying that perforating is a critical and enabling technology for hydraulic fracturing. 120-degree or 60-degree facing are the most recommended for hydraulic fracturing. And as we mentioned, use multiple clusters. Having a uniform hole size is paramount for hydraulic fracturing. And looking at the average entrance holes data, as we discussed, is not enough. Check the data of the individual shots and the standard deviation. And work with trusted vendors willing to conduct representative tests. Be aware that the different casing grades or casing sizes will yield different entrance holes diameters. And use data from representative tests when possible. And performance, efficiency, and of course cost are critical for the planning of multi-stage completions. With that, I'd like to finish my presentation. This is the list of references that I have, so that you can go and explore more about these topics. And I would like to open it now.
Thank you so much, Jorge. It was a wonderful presentation. I hope all of us really enjoyed and grasped the things that you had to convey to us. So let us now go to the chats. Alex, please.
Yes.
Go over and check what are the questions there.
Yes, Jorge, thank you. We do have a few questions here. The first one from Celine. How can a consolidated formation be weak, knit clear?
Yes, there's a lot of formations that the rock, it is consolidated. You just have a low unconfined compressive strength, a low UCS. And what happens with those, you perforate, and as the reservoir pressure starts going down, the effective stress increases, and eventually the perforations might collapse and start producing sand. So there's a lot of cases of wells that produce sand, but the rock was not completely unconsolidated. It was actually some competent rock. You can take a core of it, but it is likely to produce sand, and the main reason is because the perforation tunnels collapse and get, when exposed to shear stresses, the grains starts coming loose. And you know that by looking at the UCS of the rocks.
But sorry, follow-up question to that. You talk about UCS. At what point you are going to find out about the UCS, uncompressive confined strength, right? Is that what UCS mean?
Yeah. I mean, there's. I'm not a geomechanic expert, but I mean, you can find the UCS. You know, the best way is by taking some cores, taking them to the lab, and in the lab they do a test of the unconfined compressive strength. But also, you know, the petrophysicists will tell you some methods that they have by looking at the sonic logs and the log data that they can estimate the UCS of the rocks.
Because if you have to do the UCS in a lab with the core, you have to have a lot of disciplined, organized, and pre-planned study. And in many cases in the world that I know of, and maybe many of you can vouch for it, not all of these things are done in an organized fashion. Am I right on that?
Yes.
Yeah, if you have the petrophysics, I think sonic log, like Bob Barbe is an expert on that. He may be able to shed some light on that. I don't know whether he's in at the moment there or not.
But yeah, I know that we rely normally on the geophysicists to look at the sonic logs, and they can also look at the other information from the drilling program that can give them a good idea of the UCS of the rock.
Well, at the moment, I think Mamdu, you are there, right? At the moment, you are a petrophysicist as well. What is your comment on that?
Yes, if you can hear me. Yes, actually, the sonic logs, particularly the combination between compressional sonic and shear sonic, and if you are lucky, if you can get oriented shear sonic dipole sonic, then you can calculate all forms of stresses and find out the minimum and maximum horizontal stresses as well as the vertical stress. And that will get you a lot of information about the stress distribution. However, actually, I made a question to Jorge, which is again redundant question because it's answered in this comment I'm making, that this is all related to the porosity, permeability, and the degree of cementation of the rock. And also varies with lithology, being carbonates versus sand versus shale. So again, it is a lot of actually the rock mechanical engineers and petrophysicists working together can give you.
Okay, thank you.
Yep.
Alex, next question, please go ahead.
Okay, we'll move on to the next question. It's from Carlos Pineda. First comment, Jorge, awesome presentation, thank you. I know the objective in unconventional wells is to create the flow path area for the hydraulic fracture, which you can achieve by the phasing and the number of holes per cluster. But since the perforations are going to be eroded, are uniform charges really needed?
Yeah, that's a good question. You know that they're going to be eroded, but you want them to be eroded more or less equally, and you want the initial conditions. It's going to be a dynamic process, but you want the initial conditions to be the same for all of the perforations, and so that all of them take about the same amount of fluid, and you have a process important. Like in the figure that I show, if you have some holes that to begin with, they are not uniform, it's going to be a domino effect. The ones that are larger are going to take more fluid, which are the ones that are going to get eroded, and they're going to be taking more fluid from there on. So that's why, from the initial conditions, it is important that all of the perforations in all of the faces have the same diameter. And if they have erosion, you expect them to have more or less the same erosion in all of them.
Jorge, I have another question for you, if you don't mind.
Please. Sure.
You mentioned in the presentation that for horizontal wells and for unconventional, your target is basically uniform short fractures. However, again, it's common perception that engineers, especially production engineers for hydraulic fractures and for productivity, they will aim for a deeper penetration for the rock and longer the best frac height and best frac penetration to increase the surface area of the hydraulic fracture. So what or how your small uniform entry fractures or in the initial hydraulic fracture will fit into that big picture?
Okay, so let me see if I understood the question. The question would be, is more related to the facing or to the number of perforations that you want to have in there?
No, to the frac height and frac length.
Okay, and well, in the case of a horizontal well,
yes.
In the case of a horizontal well, let me go back to that one. You know,
yeah.
The fracture, you know, independent of the fracture length that you might have, is always going to be perpendicular to the well and to the zone that you just perforated.
Yes.
So as opposed to the case of a vertical. What was the vertical? Yeah, in here you want to have a long interval, and because you want to perforate, longer perforating interval than in a horizontal well, because all of the holes are going to be exposed to the frac around the near borehole. Of course, the fracture is going to grow bigger than the perforating interval in this case too, but you have more holes for the fluid to come through there. But in the case of the horizontal well, yeah.
Mm-hmm.
In this one, really, as long as you have, in fact, some people say that in these cases you only need want to have limited entry control for your limited entry. So you are trying to control that one. So on this one, really, the facing honestly is not that important. It could be, you know, any facing that you want. The whole idea is just to have the perforations, all of them closer together, so that when the fluid comes into the well, they can easily and without too much tortuosity get into them. There's new gun systems that actually they have all of the three charges in the one plane. Those are fairly new systems. There's only a couple of vendors that have them available today, but I think it's a good idea. Now they use smaller charges, so the holes that they create are not so big, but in many cases that is enough. But the whole idea, to answer your question, I think, is what you want is the facing in itself is not so important. What you want is all of the perforations to be closer together, so that when the fluid comes in from the fracture into with that answer.
What's the impact of natural fractures on the perforation in this case?
Oh, natural fractures. If there's some natural fractures in the formation, then the fluid, the fluid might. I mean, for the perforations, it doesn't affect them. You're going to perforate this the same way. But if they contribute, the fluid coming from those, depending on the place, they may have some tortuosity to get the perforations.
Thank you.
Alex, continue with the next questions, please. I think Bob Barbe is here. Bob, you can unmute and you can participate as well if you want to, please.
Okay, can you hear me? Yes, sir. Our next question here is from Francisco Pineda. Is centralization of the gun important?
Yeah, it will be beneficial, definitely. If you can centralize the guns, they tend to give more uniform hole size. The problem is that the centralization of the holes is more expensive, and it's another component that you need to put in it. And if you're doing in horizontal wells, going with centralizers through all of the deviations and so forth might not be the optimum. Sometimes just to put a standoff on the guns could be beneficial. More than centralizing the gun. Remember, you're going with a very long string and with multiple guns. So one way that the industry has done actually to prevent the use of centralizers or standoffs, which are available, and that is one option, is just to develop this new set of charges that they are less sensitive to the water clearance. But yes, to answer your question, sometimes. In fact, sometimes I have recommended to you to put some standoff in the guns just for that same reason.
Okay, our next question here is from Celine. Will you start with a deep penetrating perfs if you would do hydraulic fracking?
To me, the only reason why I would use a deep penetrating charge is because some of them, they tend to give more uniform hole size for the water clearances that we normally face. So I'm more interested at the hole size and the uniformity of the hole size than the penetration in itself. Really, for if the wall is going to be frac, the perforation length is not so important. Some people believe that it is. I don't think so. I mean, as long as you have communication with the wellbore, is all you need. In fact, think about the cases that we now are doing very often in long horizontal wells, that instead of perforating, we only use sliding sleeves. So the perforation is zero. The depth of penetration is zero. However, in fact, I conducted some tests in Rosharon about that. If the windows of the slotted sleeve are not properly oriented, you can affect the breakdown pressure. But if they are properly oriented, the breakdown pressure is the same or less than if you perforate. So orientation is what it is important, more than penetration for hydraulic fracturing.
Okay, then to you, from me, then a follow-up question. I don't know whether I missed it or not. Did you say that perforation should be perpendicular to the minimum horizontal stress?
I think I was talking for the vertical cases, and in the vertical case, for the vertical case, I said that the perforations should be in the direction perpendicular to the minimum stresses. So they will be the ideal situation, if you can, will be to have perforations that are oriented with the perforation fracture plane, that is in the direction of the maximum horizontal stress, or perpendicular to the minimum horizontal stress, as this figure is showing over here.
Perpendicular to the minimum horizontal stress, okay.
Yes, or
Because my question was that if I drill a shallow well where the or vertical stress is probably the minimum stress, and the two horizontal stresses are the maximum stresses. So in that case, in those kind of scenario, what would you do?
Okay.
Or when the stresses are isotropic, all three stresses are more or less equal.
You're talking about a horizontal well?
Let's take those both scenarios.
Well, if it is a vertical well, and now you say that sigma 3 will be you overburden, because it is very shallow. And in those cases, what could happen is that the fracture is going to behave like a horizontal well. It's going to behave like the other one, because then the fracture, instead of being oriented like this, it would be like the gap shown in here between these two layers. You know, the fracture will be now perpendicular to the well. Because you're always going to be pushing the rock against the minimum horizontal stresses. So if the overburden is the smaller one, then instead of creating a vertical fracture, you might create a horizontal fracture.
Yeah.
And sometimes we see, you know, because of stress shadowing and other effects, that the fracture could actually twist and change as it propagates. There's some SP papers that talk about that.
About the same.
Oh, if there's if all of them are the same, they typically go you know, randomly vertical, like what we have over here. But then the direction might be, you know, there's in any direction.
Okay. And are you going to stay in the breakout room later? I mean, in our network session later on?
I'll stay for a little while. Yes.
Okay. Well, Alex, if there are other questions, go ahead, please. Otherwise, we'll have to switch to the next speaker.
Yeah, we got a few. Carlos Pineda is following up to Francisco's question. Are perforating guns being centralized in the casing in unconventional horizontal wells where uniform charges are not utilized?
Yeah, normally they are not. Normally they are not, and they're not because of the cost and the number of centralizers that they use, and the risk of using centralizers as well. You know, they have to remember, cost is the main driver in these multi-stage completions. So when you need to go with 30 or 40 guns, every penny counts. And for that reason, unfortunately, sometimes people overlook all the more important things, and I can rarely see the use of standoffs or centralizers. In fact, from the people that I have talked, I think that almost none are being used.
Okay, our next question is from Russell Robbins. In addition to Francisco's, what are the common ways to centralize the guns?
The more than centralization of the guns, what they are normally used is just standoffs, and they are like rings that are put on the gun adapters between the guns that partially centralize the guns. They're just standoffs. They're like rings that go attached in between the guns. And the other problem also with those is that in horizontal wells, you know, you have the gravity, so you need to put. Now you're going with short guns, so they will go, but you will need a lot of them.
Okay, our next question is from Francisco Pineda. On selection criteria, and in quotations, choose trusty people and companies. What are a couple of tips we need to look for to confirm that they are trusty or not?
Yeah. I mean, to me, is how open they are. You know, if they invite you to look at the facilities, if you need just to feel confident with them. You know, how they present information is it just information in a piece of paper, or for example, if somebody invites you to come and witness the test and they have an open door policy, to me that is that is a trusty company. And you just need to know the people. You know, I remember George King one time in a presentation, he said, you know, for me, I don't choose service companies. I always look for the people that I trust, regardless of which companies they are. And so to me, it's a combination of both. You need to make sure that you're working with people that you feel that they're telling you the truth, that they indeed or that they can put themselves in your shoes, and or in your shoes, and that they have an open door policy. You know, test that they say, okay, we'll do the test for you, and you can come and witness it.
Okay, another question from Francisco. On performance evaluation, since the API test is done in L80 casing, can extrapolation to 110 K performed to other metallurgies such as 13CR110 or K55?
Yes, there are some correlations, and in fact, some of the software that do the modeling, and they can compensate from L80 to P110, but to me, there's nothing like the real test. You know, those and especially the API tests are expensive, but the other tests that I show, you know, the ones that are just with a short piece of casing, and you can even do that without concrete behind it. Those are fairly inexpensive, and to me, they're just better than the model.
Jorge,
Comments
thank
here
you very
from-
much.
Oh.
I got a follow-up question, Alex.
Okay, sure, Francisco.
So as you said earlier, sometimes we, in the name of saving, we overlook some important things, such as this now. If we are only spending the money to do API testing, which is very expensive, if we go and do testing for 13Chrome110, that is even more expensive. So these correlations, are they very close to the real thing, or they're not worth our time or money?
The correlations. Let me make a note. I mean, the grade or the metallurgy of the casing has a very little effect on the hole size that the perforations create. What has a big effect is the strength of the casing. So the difference between an L80 and a P110 is big. Now, whether it is chrome or what the alloy is not going to change that much. So you can choose, you have a couple of options. If you have a short section of a casing that you can get, which is the same as you're going to have in the well, that's the best thing. You take a short case and go with a vendor of shape charges and say, hey, I want to do a test of these guns in this one and actually look at the holes. But if that is not possible, as long as you get the same, another piece of casing with the same strength, I think that is the hole size, the diameter of the hole size is also very little affected by that. So the thing to watch is really the strength of the casing.
Okay, see that answer that question. Just a few comments here from Sarko Lira. That was a great presentation. Another one from Russell Robbins. Very well done and informative presentation. Thank you, Jorge. And we have a question here from Andu. Does the competence of the rock related to porosity, permeability, and degree of cementation?
Yes. Yes, I'm not a rock mechanist, but absolutely yes.
He says, yes, the sonic logs will tell us. Comment or a question.
Oh yeah, well, I know that the sonic. I mean, I'm not a. I think that Bob is a geophysicist. He has come in here, but the sonic logs can be used to determine, not only the stresses in the rock, but also the mechanical properties of the rock. And the UCS is one of them that can be derived from the logs.
Yeah, that was my comment.
Okay. Thank you, Mamdouh.
Our
next question comes from Herman Baca. Can you comment on the storage life of shaped charges, i.e. Expiration dates and performance?
Oh, yes. It's been a while. I don't remember right now, but it is few years. I think that normally is recommended something around 3 years to give them. We know that they can go longer than that, but the recommendation, I think, is, don't quote me on that one. I have to go back and check it, but it is few years. I think it's about 3 to 5 years.
And just to add to that, Jorge, correct me if I'm wrong, the way that is being stored also in the room, the temperature.
That is good for the comment. That is very important because humidity affects, especially what may affect is the liner. So normally the charges come in boxes that are sealed. And thank you for the comment, Carlos. It's very important that the bunkers or the places that they are stored, they are kept in dry conditions, and that's something that could have a big effect on the charges. The liner that I showed before, that's the one that might start have some corrosion and it starts separating because of the humidity in there. So. With the package has a seal bag, and they put desiccants inside of it to prevent that one. And they should be stored in dry rooms.
Okay, got another question here from Francisco Pineda. Would you recommend a combination of deep penetrator and big hole charges? If yes, what conditions would you call for that combination?
I know some people have been doing that, and they claim some, but it's like of a niche market. I really don't recommend that one. The only time that I would recommend that one is on the planning of some limited entry jobs where you might want to have a smaller hole size in certain clusters than another ones. In perf intervals, sometimes they have combined big holes and deep penetrating charges. For hydraulic fracturing, I don't recommend that one for the reasons that I mentioned before. You're going to have different hole sizes in the, typically the deep penetrating charges are going to have a smaller hole size than the big hole charges. So no, I don't.
Okay.
Unless it is for a limited entry job planning where you have one gun with deep with different type of charges, and that one sometimes has been done, and that is okay. But all of the charges on the same perforating gun and the same cluster are going to have the same hole size.
Francisco, we had a follow up for that, or are you good?
Yes, Jorge, you're great.
Thank you.
I've seen that combination back on my days with BP, where we had an overlapping of the casing with the liner. It so happened that part of the zone of interest was in that overlap. So they had to go through the formation damage, two casings, two strong casings, and that's when I saw the recommendation of the combination. And I agree with you. You cannot have the two different types of charges in the same gun. You have to have one gun with deep penetrator and one gun with big hole. Thank you very much.
Very good comment. Thank you.
And then a final comment here from Bob. Take a look at SPE 121972. A good discussion on work to estimate UCS from porosity and Young's modulus. And with that, we've come to the end of our questions. Salim?
Yeah, let me make a comment, if you don't mind. I want to give the opportunity to Jorge for, you really have given a whole lot of good information to all of us. Your company, LDC, and then you have Resentech. Do you mind taking 1 minute to tell us about it?
Oh, sure. I mean, LDC Energy Consulting is just myself. I offer consulting services on completions and on technology management. That's what I've been doing as a part-time. Then in Resentech, what we do on that one is we've been looking for products and services that will help our industry to be more environmentally friendly, if you want. And we have a couple of products. The main ones are related to control or reduce the amount of evaporation losses in the water storage pits that are used for hydraulic fracturing. You see, companies pay a lot of money for obtaining the water that is required, the huge amounts of water that is required for these huge fracturing jobs in unconventionals, and they put them in these big pits on the ground, and a lot of that water gets lost to evaporation. So we have a product that reduces that evaporation, and also some automatic dispensers that can do some data acquisition of the atmospheric conditions that produce the evaporation.
Thank you, Jorge. Salim?
Yes, Jorge, well, because you may not be there a long enough time in the networking session, I do have another question before we wrap up your presentation, and we have to move on to the next one as well.
Sure.
My question is that you talked about trustworthy the client, I'm not client, I mean vendor, I believe, and trustworthy, and you said also that it is better to do a testing before you do the real perforation job. So this test you will be doing where? In the lab situation, or where about it should be done? And also among the leading companies with a lot of experiences, which one you would recommend? I know you worked extensively at Schlumberger, but there are other service companies as well.
Oh yeah, and there's a lot of good service companies. I mean, to answer your first question is definitely let me clarify, is not something that you need to do for every job. What you need to do is for the planning of the gun systems in that field that you're going to be using, and you know that you're going to be to see if they already have a test that has been conducted in that specific type of a casing. And if you have some doubts or you think some conditions might change, then go and perform the test. The test normally is conducted at the manufacturer's facilities. The companies that produce shape charges, they have the land, the facilities, and the permits to use the explosives and do the tests. So you need to go with one of the shape charge manufacturers, and I think that we have very good companies here in the United States. Very good companies, very good manufacturers. But I like to work with the ones that really have a good open door policy, and that they can welcome you, and you can bring your piece of casing and witness and see the test. So,
thank you so much. Are there any other questions to Jorge before we move on to the next one?
No, I just want to thank him for this nice presentation.
Yes, it was a wonderful presentation. We appreciate you coming over and taking the time to make the presentations on all the future presentation of ours. Okay, Jorge, thanks a
Great.
lot again.
Thank you.
Shall we move on to the next one? Bob, you are there already, right? Let me
Yeah, yeah.
make you a host so that you can, I haven't done it yet. Where is Bob? Okay. So,
You got Klaus's cousin's name there, but
okay, Bob, you are now the co-host. And before you move on, let me introduce you to our attendees. The reason I'm taking the privilege to introduce Bob because Bob and I worked at Shell for a number of years together, and actually he shared an office just beside my office. So, and I'm fortunate enough probably to introduce him today. Bob has spent 10 years with Schlumberger as an open hole field engineer, sales engineer, and product development engineer. While at Schlumberger, he was the North American product champion for the frac height and QuantiFrac products that integrated wireline testing and pumping inputs to optimize hydraulic fracturing treatments. And since then, he has spent 24 years consulting to over 250 companies on petrophysics and completion optimization. He served as a SP Distinguished Lecturer on integrating petrophysics with the hydraulic fracture treatment optimization process. He has implemented this integration process in a wide variety of reservoirs in North America, conducting numerous field studies for operators, evaluating the effective frac length and recovery factors in over 4,000 wells, and providing best practices recommendations based on the study results that is noted in the SPE paper 490483. He has been responsible for the petrophysical analysis of over 50 major fields worldwide. That I would like to hand over to Bob. Bob, you go ahead and make the presentation. I'm going to put you on also so-called, so that everyone, you can be focused on spotlight, that we call.
all right.
Yeah, you go ahead with your the slides in presentation mode, please.
Got it? See him okay?
Yes, where are you in the system?
See me, but I see the slides.
I don't think we're seeing the slides here.
No, we are not seeing your slide yet.
Let me see if I need to share. Was there a button at the bottom here? Let's see.
There's a share at the bottom, yes.
Let's see. Let's minimize this guy. Okay. Alt. Okay, got this full screen. Let's see, where am I? Trying to. I hate to be outwitted by inanimate objects. Okay, stop video or no?
No.
Where's my share screen? It's hidden by the bottom of my screen.
It's spotlighted.
my control.
Sometimes it may be at the top, Bob. You put your cursor at the top.
The top.
If
Cancel, no. I don't see anything on the screen here.
No, it's on the bottom of the screen. It's a green bottom in the bottom of the screen.
Share, is that good?
Yeah, that's share screen, yeah. Yeah, it starts sharing.
You see it now? You see my slides too, or?
No, we are only seeing you still.
Ask him, he has to check the monitor in which he wants to share the screen.
Because I'm on, I can see the slides here. Let me see. Problem is I can't see the way the screen zooms. I got my control screen at the bottom with all the icons. It's covering all the buttons at the bottom.
The button is a green one. In advance and share part of your screen.
But if you do not see it, go to the minimizing type screen, and you will be seeing your buttons as well.
Minimizing the which one?
Your screen.
Which screen?
The one. Okay, we can see your desktop. So you share on share, on share, and then pick the presentation when you share.
Okay, I'm on share screen here.
I'm going to stop you from sharing.
Okay.
So now you should be able to share, but when you share, pick the slides only, not your desktop, but your slides.
Okay. I just hit share. It's not going here. This is strange.
Bob,
But you want to share. Okay, I'm doing that. I'm hitting the green share and it's not coming up.
Bob, can you do one more thing?
Can we see it now?
It did come before, no. Now we go back to the desktop.
We have your slides.
We got it now? You see it now?
Yeah.
No, Bob, you're fine now. Yeah.
Blind squirrel finds an acorn. I can't see myself, but that's all right.
Great, thanks.
Okay. I can find out how to put my little deal there so I know I'm looking at the thing okay. But I can't see my own deal, but that's okay.
You're not seeing your own slides, you mean?
I'm not seeing my face, because I can see that I'm looking at the camera okay. I think I'm okay though.
Yeah, it's okay.
Well, you're a spotlighter, so everyone is going to be looking at you. You go ahead.
Okay, so everything's good. The slides look good. Okay, thanks a lot for allowing me to present today. I think this is an important topic because refracs are, I think, finally this time around after the first two rounds didn't do too well in organic sales. I think this is probably the time they're going to really make a difference. And any company that's got refrac opportunities really needs help on this because it's somewhat of a new deal. So this is a very good topic for the industry right now to be looking at, because that's why I'm saying this. But the big question we get now is, since the double black swan, everybody was gung-ho about doing all kinds of stuff, and then all of a sudden it's like, whoa, what do we do now? And the question comes up, can you make refracs work at these current prices? Because it's definitely a challenge. And so the challenge is to make sure you can do it right, do it efficiently, do it at the lowest cost possible, and get the best results possible. And I think we've compiled enough information here to where Jorge was talking about with the limited entry perforating is probably one of the key aspects to that. The XLE method, when it's used properly, can really save a lot of money, and we'll show you some examples of that. Okay. Some of the key takeaways from this, really, as I just mentioned, getting your costs down while maximizing recovery is critical. There's really not a lot of room for slack with the pricing environment that we have right now. You got to get it right, and you got to do it at the minimum cost possible. And we think there's a unique opportunity here in organic shale wells because, the history of the wells, over time, with the cluster spacing starting out on very broad spacing and then going to very narrow spacing, seeing increases in production as a result of that. And what's in these wells, which is a key part, you can actually get superior returns to new well drilling completions, or at least competitive returns that are equal to it at a much lower cost. And you've got a potential to significantly improve your field economics with XLE and also mechanical isolation. And mechanical isolation with either expandable liners or cemented casing will work. However, the mechanical isolation is a lot more efficient and a lot cheaper overall, even though it seems like it's more expensive up front. Biggest opportunities we're seeing right now in this environment, the pure gas plays, assuming gas does hold up at least a little better than it is right now. But, you know, Haynesville, Marcellus, down to Eagleford, we've run some numbers on several of those wells, and it looks pretty good right now. It's somewhat immune to the oil issue. But then also in the oil window, and the Eagleford looks really good, and also the Southern Midland Basin looks good. Really pretty, a lot of the Midland Basin does, but the Southern Midland Basin especially, because that was where the first development took place, and that's where you've got the widest cluster spacing out of all these. A lot of the wells in the Northern Midland Basin already have fairly close cluster spacing, so you know that's really going to minimize some of the activity there. But I think down the south there's a lot of opportunities, and we'll show you some examples from that area. Find a place to have the meeting, and well, I guess Urtex said it's the speed. I just found out is going to have to move from the convention center as of yesterday. So, at any rate, wherever we present it, it'll be presented there. So, questions: what do Refracs and Rodney have in common? And I think everybody's familiar with Rodney. You know, don't get no respect, right? Well, Refracs kind of have been in that category for a while as well. You know, we had two down cycles, 09 and 15. We saw a huge increase in refrac discussion. I made a joke numerous times that, yeah, I think I've gone to more refrac conferences and I've been involved in major refrac projects, and it's really a true statement. I've taught more refrac courses than we've been involved in major refrac projects. You know, one-off deals are fine, but I think really we'll see from where we're going with this that you really have to have a program. You have to be consistent. You have to, you know, do more than one, and there's a lot of benefits to doing 5 or 6 successfully. 2015 annual technical conference, and I think it was in Houston, basically showed that, you know, how to dump diverter to get effective refracs, you know, and really that was essentially, you know, random, and you really can't have that. You know, there's a huge risk involved if you can't predict your results on these, especially if you know the oil in place is there, and that was done mechanically inefficiently the first time. But 2017, you started seeing a lot more papers and a lot more interest on mechanical isolation. Halliburton had an excellent one. They did the Haynesville and then the Eagleford. I think they had about 70 wells where they were cementing 3.5, which we don't typically. That, you know, we got to do this. We've been telling people this for a number of years now, and I think finally everybody's catching on that just dumping junk in the hole to try and do a refrac on an organic shale well with, you know, probably up to 1,000 perfs sometimes is not really very effective. You really got to isolate the entire wellbore and reperforate just like a normal frac. You want to do it like a typical new completion. There's really no difference in the refrac design than in new frac design other than perforation placement. You've got to be careful. You definitely have to have close perf cluster spacing to be able to charge the old perfs and break down new rock. But the results are now very consistent across the board. The current prices we're talking about, you know, everybody's looking at the $30 price, $35, $36. This was 10 days ago, so I mean, it's probably changed since now. But as of the 24th of May, this is the forward strip that we're using. And, you know, you look at it, it's, you know, it's doom and gloom right now, but it's coming up. And both the oil's coming up, gas is staying fairly flat. But, you know, all your economic analyses are going to involve present and more importantly, the PB20 for your PUD value. If you can get PUD value for your behind pipe reserves with refracs, that's a home run. Nobody's done it yet that I'm aware of, but then again, nobody's really had nobody's had a systematic refrac program. A couple operators have done that, and I visited them last week trying to find out if they were looking into this aspect of it. And one of them got back to me and said they hadn't been, but it was something that was interesting to them. But, you know, the current spot prices, you know, you're not going to get all your oil back today. So really, you know, trying to make something economic at $35 oil probably isn't going to work. But if you look out, you know, in the future, you know, the future cash flow stream, you know, is good. You know, you look at like the Marcellus, for instance, one of the executives over at Range was telling me that they're allowed by their auditors to book 55-year production times. And we looked at a lot of wells up there, and at 30 years, a lot of them are still positive cash flow, you know, especially because that stored gas is kicking in and flattening out the decline curve. So, you know, it's not all doom and gloom in that respect, you know, across the board. It's not good, but it's not the death of it either. It's kind of a comical thing, you know, but yeah, let's make America's old oil and gas wells great again. You know, in the gas wells especially. Right after the price crashed, we got several inquiries on refrac projects in gas zone areas, Marcellus and Eagle Ford gas. And we did a little project in the Eagle Ford gas just recently, just looking at that as a potential area, which is a very, very good potential. Especially because in the Eagle Ford, that was some of the earlier wells were there. The first organic shale wells on the Gulf Coast were 2008, you know, 80, 90 foot cluster spacing. You know, we're on 12 to 15 now. So basically, the key talks about how we came up with this. I don't have it in here, but anyway, it's Urtec 2660, I think it is. But we looked at organic shales in the Eagle Ford, Marcellus, and Permian, and what we're seeing is with close cluster spacing, and it's somewhat predictable, you're getting more and more like a conventional tight gas or tight oil reservoir. You're getting more and more of your reservoir being continuous. You're not totally continuous yet, and I don't think we're ever going to get to that where you have 100% SRV. I don't think it's mechanically possible. But if you're down on 15-foot spacing and you have a somewhat complex fracture from your thin fluids and your stress shadowing, you're getting almost a complete coverage of your area. The SRV emulates a low permeability conventional reservoir. And the number we came up with, 13.5, 13.7, I think it is actually, for the number of the cases that we did in the oil, is getting awful close to that 15%. Should it be 15%? Well, maybe if you could get 100% coverage, but one of the operators I was talking to in the Eagle Ford was saying that they started following the logic on this a while back. And in fact, the operator that was presented the Eagle Ford pressure example I'll be coming up with here, they actually were thinking about going to 1 foot spacing, and they went to some very short spacings and it was hard because mechanically you're starting that your stress shadowing is not your friend at that point. You tend to start having mechanical issues between your perforations. So I think the 13.5, 13.7 range is probably going to be our range that we stick with. And then the gas reservoirs, we're seeing it's similar. You're looking at probably 70% recovery factor on some of these really low permeability conventional reservoirs, and we're seeing right around 59% on those numbers. So, which is good because that tells you what you should be getting out of these if you have a properly completed well with close cluster spacing. So whatever you have already and versus that number is your refrac EUR, which is a very important number. If you got a really high EUR and it was mechanically inefficient, it's probably a very good candidate. So, and we're looking at, basically we have numerous economic opportunities even at the current depressed pricing in all 4 areas. So, you got as much as 90-foot spacing on some of these early wells in the Marcellus, Eagle Ford, and Haynesville. I guess that didn't get the memo that it takes a gas molecule 100 days to go 1 meter in 100 Antarctic rock, but at any rate, we realize that now, and we're down around 15 feet or so. And then again, we also in the oil, because oil is depressed, but quite a few opportunities. Larger cluster spacing, once you get up above 40 or so, there's really no real rule of thumb on that because it's a function of your cluster spacing and the OIP that you're accessible within the mechanical boundaries of the frac. And the mechanical boundaries are very important too because all fracs don't have the same height. We found a very strong evidence in this last study that your height is limited by the mechanical boundaries within the organic shales, and that you can get consistent recovery factors if you put that as your drainage height. This is an interesting slide. It was put. They did extensive involved study they did, and they were saying that with 10-foot cluster spacing, you ought to see about a 13.5% recovery factor. Well, we took everything under 20 feet for our sample, so we don't really have a good average, but we're probably averaging around 15 feet or so, and we're right there. And then you go out and we took a 10-well sample with large cluster spacing and took the average of that. We're at 4.6%, and look where it falls on that plot. It's not too bad, huh? So I think they're confirming what we're saying is that as you're getting clusters closer and closer together, and the same should follow for gas. I mean, you don't have enough data you know, to nail that down. We just really literally started looking at gas again about 2 months ago after putting it on the shelf for a number of years. So we're still getting back up on the learning curve. I had to go back and dust off my notes on the stored gas and calculations and all that, because I've kind of forgotten that since 2010 when we did it last. But it all works. Here's another plot from Hongji's paper. Showing cluster spacing depth. It's all about SR. Here's the increasing SRV is going to increase your EURs. That you know, that relationship is, you know, not even being questioned anymore. But, you know, how do you get more SRV? Well, you decrease your cluster spacing, but then also submit that you have to have high cluster efficiency, and that's where the XLE comes in. So this is the example I was talking about that was done. The ConocoPhillips did it, presented at the ICOTA pressure monitor well. I think it was one of the first ones they drilled in that big study they did. They just recently, they published this at ERTEC, the results of other wells at ERTEC. I didn't see this one at ERTEC 2 years in a row. It was a big laboratory they had down there, but 70 feet away, they had a pressure monitor well. And pretty much the majority of the depletion, and I talked to one of the guys last week that was involved in the study and said, yeah, well, we still had a little depletion outside of that. We just didn't, you know, that you know, kind of generalized it a little bit. But basically, you're looking at, you know, from that, about 7.5 foot of, you know, high drainage with low pressure. There was some low pressure around that. So, you know, it's not 7.5 feet is all you're draining. But the majority of your production came out of 7.5 feet of a 50-foot cluster spacing, which tells you there's some huge opportunities there, because basically you got 85% of the rock producing little or no production with the large cluster spacing. So this is a key slide for refracs. But then again, you know, should you go closer? And that's what this is the same company that was talking about. I don't know if they actually did it or they just talked about it, but they did go down at least 7.5 feet, I believe, on one of their tests, and started really didn't see much increase. But I think part of that may have been the mechanical interactions between the perfs. I think you start, you know, clusters, you know, your clusters shadowing, the stress shadowing between clusters, you know, the interaction between clusters, what I'm trying to say, you know, is positive in some respects because it does give you more complexity. It tends to steer your fracs away from the initial maximum stress direction. But if you get too close together, you can actually have perfs shutting each other down. That's probably what's happening as you go down. I think your mechanical issues are going to. So operators use 13 1/3 just to have 3 clusters per pipe joint. But you know, nonetheless, as long as you're down in that range, I think you're probably going to be okay. Particularly in refracs, because you want to also get close to the old perfs. So if you got too wide a cluster spacing, you might get some of the new rock, but you've got to recharge the old perfs because you've got parent-child or primary infill. I'm sorry, primary infill well interactions to consider there too, because usually you got wells around. This is historical cluster spacing. You can see here it's saying Marcellus 50. When I was working on a project up there, we were at 90. The Eagle Ford's at 72. The first the 7.5 foot drainage on. So, you know, that this is exact. Eagle Ford was where the study came from. So there's definitely some opportunities as far as undrained rock. The only question is how much oil in place is within that undrained rock. Just having a low recovery factor does not by itself make a refrac candidate valid. It's got oil in place as well. And how big is the size of the prize? Well, the detailed study we did was in the Southern Midland Basin. And we saw from that initial chart that Hongji put together and with our numbers that about 40-foot spacing, you've got basically, you know, you're going to have less than half the oil done. You know, is that a good number? Well, you know, really, it's a fuzzy number, really. But, you know, your opportunities are much better over 40 feet, we think. Under 40, probably not. But 38% of the wells had that. So it's a fairly large population there. Are all of them going to be good refrac candidates? No, but I mean, you want to start with that probably. Here's an analysis that we did AFEs on these 10 wells, put them all together. And now this is using the historical AFEs on these wells. We took actual AFEs from the university lands and started with that number, and they were higher than this quite a bit. In fact, we got a call in during one of our talks about a month ago from an operator that was doing Northern Midland Basin wells. Says, hey, our fracs are costing us $4.5 million. Where'd you get this $3 million estimate from? And I said, well, you know, that's the numbers with the new, with the XLE, and also with the current, you know, we've seen about a 15% reduction in overall pricing since the end of last year. And most of those AFEs are from last year. And we went back and looked at it. They were on 10 foot, they were doing 10, 15 foot clusters, which, you know, was basically 9 barrels per minute per cluster. Do you need 9 barrels per minute per cluster? It doesn't hurt, but you can also go down to 6. If you go down to 6, you can do 15 or 14, you know, depending on whether it's a refrac, you can probably get 14. On a new well with new 5.5, you can probably get 15, you know, clusters in there. And you start putting those numbers in there, and then you start looking at the price deflation. You know, the price of sand, you know, a year ago was, you know, about $120, $130 a ton. You know, it's down around the 50s now. You know, same with all the stuff that's going on out there has dropped. So you're looking at historical numbers. Oh, and also, you know, going back to his story, we basically found out that if you did the apples to apples with his 4.5 million, just going to XLE alone, dropped that to 3.5 million. It's a huge savings by doing that. And then with the price deflation, you're down around where we are. So, I mean, our numbers were pretty much in agreement with their 4.5 million number when you compare apples to apples. But anyway, there's our numbers, about 2.9 million. There's our price strip down below. What does that mean as far as economics goes? If you look at your EUR, again, the refrac EUR is what the current cum production is, you know, subtracted from the 13.7% recovery factor for a, you know, basically a high cluster efficiency, closed cluster spacing well. And there's our numbers for and you're looking at some of them 12%, 18% rate of return, 21%. We chose the last 7 with over 25% rate of return. The first 3 ones are positive, but really not, you know, I wouldn't do it. And then the other thing is the NPV 10 is one thing, and that's the thing everybody focuses on, but you'll see the NPV 20 is also important for offsets that have similar characteristics. That's the value of a PUD. And so if you can get enough of these to show that PUDs will work, that's a real number that you're going to be looking at. So, and really it's not related to the current production. There's your current production there. The PV10 of the proved developed producing for the entire batch. Current value of really big cluster spacing well, I think it was 80 foot, you know, 91% rate. So, at any rate, the numbers look good. And this is at the current that I showed you earlier. So you can see the numbers are positive. Here's the candidate summary. Your total AFE for about $20.5 million for those 7 wells. Your NPV 10, and that's NPV, so it's PV 10. It's a PV 10 of $46.5 million, but an NPV 10, if you subtract the AFE, 26 million. Well, then the big thing, and we'll talk about here in a minute, is that if you get a third-party reserve report from a accredited reservoir engineering firm, and you can start claiming PUDs, and they've got about 75 offsets that have 40-foot spacing or better out there. Well, actually, we just assumed that half of the 38%, half of the ones that we saw with 40-foot were going to be candidates. That's a big number. And then your total NPV is 159 million for a $20 million investment. Now, today's prices, that's a pretty good deal. Sort of like the Dire Straits song, right? It's money for nothing, you know. Actually, it's not nothing. You got to get a reserve report. But has anybody done it yet? No, but no. But he's done a program that satisfies the so this came from Samantha Hall application at the reserve and they're not and then should establish a reasonable certainty that you were pretty much rolling the dice every time you try to refrac with diverters. Once you started going to mechanical liners, then the candidate selection program enters into it. If you choose for candidates with mechanical liners, but if you combine the candidate selection process we're talking about here with them, you got it. It's the magic bullet, and you should be able to generate a large number of the successful refracs with this. And we think the number's 5 to 6. How do we know that? Well, horizontal drilling that came in, Dennis Belvio and Shale Canada had a paper back in 895 that said 6 was pretty much it. Tim Lecision at Frac Knowledge has done a number of refrac studies. It's usually about 5. And then Exxon and XTO had a 70-well refrac program. Now, granted, these were diverters, but the first 5 wells failed. Here's that their paper. Basically, it's a good thing they didn't stop after 5 failures. This came from Mike Vincent's talk back in 2015. But you can also see on this, these are all diverters, all Bakken diverters. And I was at the paper when he presented this up in Banff, and I'm looking at it, and this was right after Bud Brigham had started doing the horizontal multi-stage fracking in the Bakken with the with just doing plug and perf, just a bunch of stages. And I said, isn't this in the same area that Brigham's operating? And well, yeah. Well, so, their IPs are quite a bit higher than this. This is all. You're saying they're successful, but y'all aren't raising the bar very high, And this is the result of diverters. I mean, you can see what's going on. You got 100 barrels a day, or 1,000 barrels. Some of them are not too bad, but by and large, it's fairly random. With this type of results, you're really not going to book reserves. But again, the key thing is you got to do more than 5 to get to this point. But the key point, the key point here is that if you do it right, if you're using diverters, you're not going to be able to do this as well. Some of the isolation options, because isolation is critical. Basically, you can use diverters and expandable liners are the only 2 options. You use XLE and expandable liners, you get fewer stages than cemented liners because you get higher pump rate. On organic shale, you're probably lucky to get 50 barrels a minute. Whereas if you go into the expandable liner, you got a 4.1 inch ID, you get about 85 barrels a minute. So what that's going to do is give you a much lower cost. Now, expandables cost more up front. That scares people off. You start telling people $75, $80 a foot, and then you're only paying $25 a foot for your 3.5. Well, you got to cement the 3.5. You got to all these things, and then you're going to end up with more stages because you can't stimulate. Without having a big ID, you can't stimulate it. And the ultimate goal is lower cost per barrel of oil because the price is low, but you got to get the cost down. Anyway. And again, it's got similar benefits to new well completions. There's no reason not to use XLE on new wells, and we strongly recommend it. Here's a comparison on an Eagle Ford well between a 3.5 cemented and a 4.1 expandable. You can see you can go from 35 stages to 27 stages just by going with XLE and expandables. And of course, we're assuming you're using XLE on the 3.5 cemented as well, but most of the time operators are not, so that you probably need even shorter stages with that if you don't use XLE. But at any rate, that's the numbers. You can go from more clusters per stage with more rate, larger stage lengths, and we'll show that works as well. Question we got with larger stage lengths, and we always get pushback on this because they say shorter stages, we're getting higher and higher results. Well, what's being ignored there is it's all about cluster efficiency. If you can maintain your cluster efficiency at a high level, your stage length is somewhat irrelevant. Because this is a paper done by SM Energy up in Howard County in the Wolf Camp. They presented at the HFTC in February. They increased their stage spacing 25% and actually looks like a little better coverage as far as cluster efficiency. They nailed down the 2,000, 3,000 pound, and really 3,000 is where we want to be on that. The initial work that came out with Paul Weddle, was excellent work and was suggesting 2,000 to start with, but then they also said 1,500 pounds delta P at the end of the job after post-erosion. You all talked about erosion in the last talk. But post-erosion, 1,500 pounds. If you start with 2,000, you can't get 1,500 at the end of the day. So we stopped using the 2,000 number and went to whatever it takes to get 1,500, and we were coming up with 2,800. And the empirical data from these tests, and not this one partially, but then the next one we're going to show you pretty much nails that down. The one that was done by Devin. Showing that the sealed wellbore pressure numbers suggest that 3,000 is the number you want to start with. I know they talked about equal entry holes in the last session. Those are important. And they talked about interstage diversion. Really didn't help breaking now new rock, but it did help redistribute the fluid and proppant among active clusters. This is all from fiber optic Warmback data. But I'll show you the one from Devin a little bit later. The primary challenge is 100% of the new rock, and fractured and recharge 100% of depleted intervals. If you're not dealing with a primary infill, like if you got a well that you're not going to be, you don't have any infill primary, or what they used to call parent-child issues, recharging is not critical. But the problem is, if you don't, you want to be able to hold your fluid from going back into these old intervals. In that case, not so much to recharge them, but you want to be able to restrict the flow, and that's where XLE comes in. But you want to use best practices. Kind of goes without saying. And then basically you get higher pump rates, you're going to be able to get longer stage lengths. And then historically we've seen these with XLE, 85–90% cluster efficiency is fairly common. It said next slide. It was actually the previous slide. So this is a comparison between this cemented liners, 5,000 foot lateral and 7,500 foot lateral. Quite a bit, and when you probably are. But if you did it with the, if you did it with the XLE and use that strategy in 6 barrels a minute per cluster, you can get it down to 3.5. On the execution side, again, we propose 13.3 to 15 foot short spaced clusters, and again, SRVs. We know this pretty much from a lot. And what we also prevent, and I'm not sure how this dovetails with the last talk, but we're proposing, based on Paul Weddle's work and just what seems to make sense, to go with one perf per cluster, and then uniform hole size is still important, but then also shoot for the 1,500 pound post erosion, with a discharge coefficient of 0.9 versus your pre-erosion. But the pre-erosion needs to be about 2,800 to 3,000 pounds just to get the 1,500 pound number. But then the work that was done by Devin, by Kyle Hosvite, showed that was really the number. That is the real number. On a refrac with an expandable liner, with 85 barrels a minute, you can do a 7,500 foot lateral with 38 stages, and versus 47 stages if you're limited with a 3.5. You can do a little better with a 4-inch flush joint. Those are tricky. They're hard to get. The 2 companies that are using them down in Eagleford had to order complete mill runs to be able to get to use them. They're not something you call Joe's Pipe Yard up and get over in the afternoon. You got to do some advanced planning, and they're a little tricky. And you still are better off with the expandable. It's the delta savings is not as much, but anyway, you're still better with the expandable. Again, it looks like it costs more up front, but then the incremental return on investment is pretty good. So when you get a bill from a quote from the expandable guys that said $75 a foot, and you're going, well, wait a minute, I can put this 3.5 in for 20. That's not the end of the day cost, because you're going to have a lot more frac stages, and more frac stages means more dollars, quite a bit more dollars, as you'll see from the slides before. Here's what we're talking about for the expansion process. Again, there's several vendors out there have this. I'm showing you the one that happens to be from Inventure, but at any rate, they're all fairly similar in terms of the way they work. Basically, first time I saw this, I thought of a python swallowing a pig. Very, very neat, huh? You can do 5,000 foot lengths. If you got a longer lateral, you can run more than one pipe. Perforating best practices. Again, what's really changed this is the fiber optics. When you're able to see downhole real time, really has changed a lot of these views. All these XLE papers came out as a result of fiber optics. Basically, the 2 papers, again, those are both Paul Weddle's, and I think one was a Shell paper with Paul Huckabee's paper. 2,000 pound minimum number, 1,500 pound at the end. The 1,500 pound is held up pretty good. That number, has been borne out by subsequent studies. The 2,000 is not, though. Again, that's too low. Taking your discharge coefficient from 0.7 to 0.9, if you put that same 0.9 number in there, it's going to give you less than 1,500 pounds. So you need the 1,500 pounds at the end of the job. And that's when you typically do your step down test too. So when you want, if you don't have fiber in the hole, probably the best way to verify your cluster efficiencies with a step down. And the reason the 1 shot per foot is nice there, 1 shot per cluster is nice there, is that you get a cluster efficiency and a perf efficiency at the same time. You don't have to guess which clusters are in which perfs, or vice versa. The other thing too is just, I don't know if this was talked about earlier, but a single hole entry point, you'll get a single fracture. If you have more than 1 entry point, They will coalesce if you're less than 4 wellbore diameters, and people have going down about 2 wellbore diameters now. They'll coalesce, but you still create a fracture at each perforation. And they have to come together. So would you rather pump that stays 1 fracture, at least until the complexity hits from the shadowing, or would you rather pump 4 or 5, and then, or some people are still using 6 shots per foot, 6 individual clusters that are very, very narrow, and your wellbore is going to be a lot higher if you have multiple perforations than you are than a single cluster. And you want to have as much energy going into the rock as possible. There's no reason that you're choking it back with the XLE to start with. There's no reason to limit the amount of pressure that's going into the rock by having inefficient perforating. So that's where we think the 1 shot per cluster is going to be good. We may be wrong, but I think it seems to make sense. And I'm sure we'll get some comments on that because we've got a perforating group out there. Good, uniform sizes are good. Cluster, if you put, it's possible you might not need the uniform size anymore. I would still recommend it just to be sure. You don't want to mess around with this, but it's possible because you tend to have uniform size if you've got the gun on the bottom and your same size casing all the way. Of course, you're probably going to get similar hole size on the top with that, but once you go to more than 1 hole, that all bets are off. You have to use uniform hole size. And 6 barrels per minute. Recommend the
Bob,
numbers we're seeing from critical. Nobody's going to that. Yeah.
You are breaking up quite often. Is there any reason that you know of? What speaker you're using? Computer?
I think it's probably my internet. I've noticed I've got all my doors open between me and the router, and I got a couple things that flashed that said my internet connection was weird, which is strange. I've got Spectrum 200 megabyte gigabyte, so that's probably it.
Is there any way we can fix it? A quick fix or no?
Probably not the internet. No.
Okay.
Yeah, I'm pretty sure it's not the speaker because I've given about 4 or 5 of these and without any problems. I didn't give them at this location though. I'm going to need to move my router closer to the. I probably need to move my router in the same room. I guess that's what's weird.
Okay, so it's late at this point. Go ahead. Yeah, continue.
Yeah. Sorry about that. I apologize.
Sorry for the interruption. Yeah.
No, it's very good. We'll go a little slower just in case,
Yeah.
We're releasing all these slides will be released. There's nothing confidential here. It's all been released by the operators that we've worked with.
Okay.
In fact, the study that we did involved 197 wells, and it involved using operator data. So we didn't have to use any kind of allocations or any of that. So it's pretty good data. But again, none of the data has any operator data, any operator identifications are in there at all. So it's all released. But the 6 barrel a minute per cluster is a good number. We frack a lot of wells with this process called Wells X, with basically just using fresh water or KCl water, and we're pumping fly ash with all. We frack to any number of formations using this at 6 barrels a minute. Over all these clusters, though, too, you have to divide that by the number of clusters to get you your rate per cluster. Most of these organic shale fracs are being pumped at 6 to 10 barrels a minute. Which then back in the day, you think that's too low. Normally you don't design frac jobs for that rate, but any rate. But typically what you're looking at, if you do the delta P calculation on these and you come up with a number, you'll find that the 6 per cluster is what overrides the delta P. You may say you can go 18 stages or 18 clusters based on the numbers on the delta P, but the problem is you got to feed all those at least 6 barrels a minute. This was the paper I was talking about from Kyle Hosvite, where they showed it was one of the first papers that proved limited entry works, extreme limited entry works. They looked at a sealed wellbore pressure monitor to be able to see when the fluid from the offset frac hits the monitor well. And if you've got a very high volume of fluid going in prior to the frac hit, the pressure hit, that means you've got fairly even distribution. If you start seeing a pressure hit right away, that means you've got uneven fluid distribution. The next slide shows that the total perforation area on the left versus your volumes. And what you can see in the coding up there, the bright yellow is 2,500, 2,750 PSI delta P across the perforations, which gives you your lowest response. So basically, that was the longest time of any of those for the pressure from the XLE well to hit the offset monitor. So it's basically proof that XLE does what it's supposed to do. But it also shows you, if you go back and look at the 2000 to 2250, which is the gray ones, it's not quite as good. Remember, I mentioned earlier that the initial work suggested 1,500 pound. The issue there was you can't get to 1,500 from 2000 with going from a 0.7 to a 0.9 discharge. So this proves that. Basically, it says, yeah, the 2000 is not enough. You can use on these. How does this compare with engineered completions and also diversion? There's a lot of people are doing that. A lot of people are trying to do that to increase cluster efficiency. And what's interesting is that, again, it says I'm getting signs that my internet connection's unstable. Boy, I got to fix this thing. Yeah, what's interesting is all three of these techniques, engineered completions, which is trying to find light rock with either mechanical strength index or your log analysis or your Poisson's proxies, trying to find similar rock, and also using particulate diversion and XLE, all give fairly similar cluster efficiencies, which is nice. In fact, that's why people tend to run engineered completions, because they're seeing better results over wells where you don't have diversion, where you don't have some kind of diversion. So. But there's some other issues involved here. XLE, we still recommend over all three, even though you have similar results as far as cluster efficiency. Interstage diversion, if you're trying to pressurize a primary or parent well, and you want to make sure you get it pressurized. And XLE will do that because it limits the flow into each of the clusters, whereas interstage diversion may plug off a cluster prematurely and leave it low stress. You got to increase the stress in these. Engineered completions are great. However, you really have to have the gaps eliminated. I've seen engineered completions that have high cluster efficiency with 40 to 50 foot cluster spacing. Go back to the Eagle Ford slide we had earlier. That's not going to work. And the problem here with engineered completions on refracs is you've got to recharge the old clusters. If you start spreading your perfs out too far, whatever. So I mean, if you do an engineered completion, I would try to limit it to a maximum of 15 feet, but then again, you got to question if they're closer than that, are you really getting an effective treatment there either? It's you want to avoid gaps. And so I think the XLE is really superior to all three, even though all three do give you fairly similar cluster efficiencies. But new wells, sometimes if you're not worried about recharging old clusters, like in the Permian, you can probably go to 20 feet on that. But again, on refracs, 13 to 15. Critical rate versus optimum rate. Your rates per cluster need to be high enough to avoid screenouts, and we think 6 is the low end on that. Do you need more than 6 is the question. And basically, what kind of height are we going to see? Minute, which is going to be your number to start with. Do we need more rate to get more coverage, to get better coverage, to get a better frac? So if your vertical coverage is adequate at 6, then you can increase your stage length, just by feeding each cluster 6 barrels a minute. So basically, that's the upshot. But if it's not, you're going to have to decrease the number of clusters, which is going to increase your cost and whatever. But if you have to, you have to. So if you need more rate, it really you're probably what you're probably trying to do is get more height or better looking fracture, and then the first thing I would look at is probably you try to increase your viscosity before going to higher rate. You're better off at 6 barrel a minute with HVFR than 9 barrels a minute without HVFR. That's what I'm saying, because it allows you to do more clusters with the HVFR. And we recommend that pretty much in all cases, because we've seen a lot of cases, particularly in the wolf camp. For instance, out in West Texas, where you've got fairly thin barriers, but the only time you can get something that makes sense for recovery factors if you assume the frac is confined by those barriers. And that's sometimes scary. We've seen as low as 40 to 50 feet of H on some of these wolf camp wells give us 14% recovery factors. So it's, you got to watch that. But I think the 6 is good. Now, here's a case where we looked at the rock properties plot on one of the Southern Midland Basin wells. The numbers at the bottom, I think this was well number 9. So it is one of the refrac candidates. And the refrac numbers are down below. You can see the refrac EUR 355. Initial completion was 3.6%. Cluster spacing 160. So that was, this is a perfect candidate. It's got everything you need. If you had a 13.5% recovery factor, you're going to have 464,000 barrels. And so basically your 13.5 minus the cum gives you about 355. That's a pretty good target for a refrac. So simulate rock properties, which is the green, dark green, fourth from the right, and the old Eaton model, basically the new over Romance mu model, which seems to work pretty well. Is to do this with multiple clusters, including stress shadowing and MWell program, for instance, or multi-stage frac program from the unstable thing again. Well, I'm going to shoot that internet connector. Pay for a 200 gig system and get unstable signal. But your first MFRAC simulation on it at 6 barrels a minute, there's your height. It's interesting that it goes through that barrier at 6620. We would have thought initially that was probably going to be a good barrier, but it's not. And the upper one's where it goes. Well, what happens if you go to 9 barrels a minute? Say if you want to cut your number of clusters back to give it 9 barrels a minute, you really don't see much of a difference. So, in that particular case, that you're okay at 6, which is going to give you the lowest cost. If you got to go to 9 or more, whatever, you got to do it. If you're basically confining the frac to the lower half of this profile with the low rate, first I would run it with HVFR to see if that makes a difference. But then if HVFR at 6 barrels a minute doesn't work, then you're going to have to bite the bullet and go to a higher number. I don't think you need to go over 9 in any particular cases, but that's just a personal opinion. We haven't done enough of these to come up with a solid rule of thumb there, but that's probably a good maximum rate. But 6 is what we typically recommend. So kind of summarize what we do this process. Again, this is a subject of we got a 2-day course coming up on this at the end of the month. I think it's an open course. We also have one coming up first of next month for major operator. But this is the flow that we're talking about. We've talked about the results of it, but this is what we actually do. And the overview is pretty much what we've done now. That's the first part. Then estimate the original oil and gas in place on how to do petrophysics and organic shales. We think our method works very well. We know it works very well. We get very consistent results. Some of the other methods being used, not so sure about that. But we like what we do, and we teach how we do that. It's a unique process. We start with the core, look backwards rather than trying to solve it from the ground up like most programs do. We estimate the drainage height from the rock properties, which you just saw the example with the 6 barrel a minute, 9 barrel a minute Wolfcamp example. Try to see what the frac height's going to be at a time. And then estimate incremental ultimate recovery from your recovery factor analysis. And it says local recovery factor analysis. Local really just means is it liquids rich or is it gas? Because I think the number of 13.5, 14%, that number is probably going to be very similar for all liquids reservoirs, organic shale liquid reservoirs. So it's because that's what you see in a conventional low permeability solution gas drive, and that's what you should see here. So it's not just local. That's not going to vary. For instance, that we had a data set from the Northern Midland Basin and we had a data set from the Southern Midland Basin, and the numbers came out exactly the same. It's 13.7 was the P50 that we came out with. Take once you have that number, once you get that what we call EUR, refrac EUR, pick a time like 25 years, and then just go in and look at the type curve for the area. How much do these wells decline on a monthly basis, month to month? Like from month 1 to month 2, what do you lose? And then do a type curve for that, and then just basically apply that percentage, not the actual numbers, but apply the percentage decline to a initial potential that you randomly pick. You just, really you just use goal seek in Excel, but you start with an initial potential and then you apply that decline percentage. Does it give you the refrac EUR? Yes, then you're good. No, then you iterate. So You just iterate on your IP until you get a match with your refrac EUR. So that allows you to do economics, because you really can't do economics from just an EUR. I mean, you can tell if it's going to be good or not. I mean, you know it's going to be, is it a good well or not, but it's not going to tell you the specific PV10, PV20 type numbers that you need. Analyze the economics. We typically use an NYMEX strip. You might need to make some adjustments for that in various parts of the country. Like, for instance, Waha right now in West Texas is kind of, a pain in everybody's, pain in every part of your body. I operate some properties out there right now. It's not fun. But anyway, you might have to apply a percentage to that, for local conditions like Waha being saturated and things like that. But at any rate, use the best price estimate that you have going out. And then estimate the cost, using the best practices. We've talked about all these. Expandable liner is definitely the best way to go. You saw the bar graph between the expandables and cemented. Extreme limited entry, I say 2,500 pound pressure drop or higher, close to 3,000 would be good. Close cluster near wellbore. And it also get you, the step down test gives you an actual cluster efficiency, not just the perf efficiency. And then optimize your rate per cluster. 6 is the default number that you should start with. If you got a good looking frac with 6 per cluster, that probably ought to be your deal. But if you're not, if you're getting some problems, if you've got some barriers that are close to your lateral, they're going to be, making your frac not too pretty. You might need to, crank that up. 7, 8, 9. Just, and the way you do that is, basically by, decreasing the number of clusters, which unfortunately increases the cost because you're going to shorten your stages. But if you gotta do it, you got to do it. You got to get a good frac as well. So to conclude this deal, we think that you got a unique opportunity in organic shale wells to increase production more efficiently and better than new completions in some cases. And basically, we'd assumed earlier that new completions were like 2x the completion cost, and it's probably not quite that, but that was based on the initial work we did. That if you can refrac a well for half the cost of a new well, then basically, if your recovery factor is half, then you're probably going to get more oil out of refracking 2 wells than you would 1 new well. And if you can refrac it for half the cost of a new well, then basically your economics are superior to the refrac. We had several examples like that, but we didn't really emphasize that during the talk here. But you've got an economic case for running expandable liners. And of course, you combine that with short cluster spacing and XLE. A little more money on the front end, but it's basically it pays itself back fairly quickly. So expandables are definitely the way to go. And also, you've got the potential with that refracs to produce more hydrocarbons at lowest cost and could be superior to new well drilling. It's also a lot less money. It doesn't require as much of your capital budget. Your rates of return are certainly competitive. You saw that slide before. That's very. When people look at refracs, and it was funny back during this whole primary infill parent-child discussion. Everybody was saying, "Well, we got to have an economic refrac." And he said, "Well, wait a minute. If you're pressurizing the primary well and save the child a 40% loss in EUR, does the refrac well even matter that much? I mean, it's nice to have an economic return from the well you frac, but your numbers on the damage to the child well or the infill well are far greater than what you're going to get out of this one." But still, people like to do that. They like to say, "Well, I want to make money on the refrac. The refrac's got to hold its own." Okay. So even on it, when we were shown earlier that you can get good results and you can get economic results and not in looking at the parent-child or primary infill type issue. Out of those 10 candidates we picked, but again, $20.5 million, you're looking at $26 million of an NPV10. And now my internet's getting flaky again. Boy, yeah. Did I just break up a little bit? Because
yeah, slightly.
That internet's goofy. I'm gonna have to fix that. Apologize for that. Is it okay now?
Yeah, it's fine.
Because I think I'm getting just when it tells me my internet's getting weak, I think is when it's
it's intermittent, Bob. It's intermittent.
Yeah, I got to move my router. I apologize.
Yeah, I think next time you do that. Yeah.
Yeah.
Well, it was previously when you made the other 5 presentations you said.
Yeah. Boy. Okay. And the next one is really, this is new stuff, but the potential to book behind pipes reserves is a huge opportunity that just hasn't really been scratched yet. And again, I talked to both of the operators that have enough refracs to do that. One of them didn't get back to me yet, but the one that did get back to me says he wasn't aware of any programs that were going on this, but something that, I think it's just going to take one operator to do it. And I encourage all of you, get going with operators to try and look at this, because this is something that could be pretty, this could change the whole industry basically. Where refract could actually, if you're trying to increase your asset value, you got a much better chance doing it with refracts than you are with new wells. Because your new well PUDs are already factored into your economics. Your new well PUDs are already part of your reserve base. But but the problem is the PUDs that you've got PV10 on your producing well offsets, very low. Remember the PV10 of the entire group of these wells we had was like $1.5 million based on current producing rates. So the key here is if you can start showing that refracts will work and you do it consistently and economically, without any problems, that's the key part. Not have any, it's got to be predictable that you can start booking behind pipe reserves. And, that number is off the charts. It's, the PUDs at PV20 is pretty well established. How do you make a refrac a PUD? Well, you got to do about 5 or 6 of them. You got to have successful results on all 5 or 6. You have a mistake on 1 or 2, you start over. And then so you get, just like that XTO ExxonMobil deal. You got to get everything lined out of where you can predict the results. If you got erratic results, this doesn't work. But those numbers are pretty good. For a $20 million investment, what we're talking about here is basically you're looking at adding another. You're already getting $26 million out of the initial, just based on PV10 of the refrac wells. By adding the reserves behind pipe, it comes to a number that's pretty scary, but it could be real. It's very, very likely that this is a real number. But is anybody looking at it yet? Hopefully people are looking at it, but to my knowledge, nobody. Doesn't mean it's not a good idea. And so looking at that, but if you can get that program and get your reserves booked, that's good under any pricing scenario. And these numbers that we're showing you there are at oil. This is at current oil prices. So what better way to increase your asset value with the refract program, enough of them to be able to start booking behind pipe reserves. That's going to be an industry-changing event. Okay, that's all I've got for now. So we'll open it up for questions.
Thank you so much, Bob. Very much appreciated. A lot of information that you have, and I believe there will be a lot of questions. But one thing I wanted to ask you, do you have the time to be with us on the networking session?
Yeah, you start now?
No, after there's a chat Q&A session for now, but we're running a little bit behind our scheduled time. That's why I'm saying that probably I suspect people will be having a lot of questions. Myself, I do have as well. So okay. If you decide to join with us in the networking session, then probably we'll condense this Q&A session and move you to our chat networking session, where you'll be put into one breakout room and our other speaker will be put to another breakout room, and then we can choose who wants to go to which breakout room.
Okay,
does that work for you?
Yeah, sure.
Okay, then Alex, go ahead, take over and see what the questions are in the chats, and then place it to Bob, please.
Okay, just a moment to get some private messages here. I guess the first one is from you, Salim. It's 5 failures were due to what? How do you make the rest successful?
Are you talking with regard to the ExxonMobil?
Yes, ExxonMobil one, yeah.
Yeah, those were all diverter jobs. Those were pump and pray. In fact, I'm not even sure they used diverter on the first few. Some of the Bakken initial refracts were not even using diverter. They were just pumping into these slotted liners and hoping for the best. So all those results from that ExxonMobil program were all pre-mechanical liners. Those were all diverters, which are tremendously inconsistent. So that's why, primarily.
Okay, good.
Okay, and the next question here is from Salim again. How do you define cluster efficiency?
Good question. Ideally, you want to have a like SM had in that paper I referenced there on the Martin County with a 25% stage length increase. Ideally, you want to have probably a fiber optic is the preferred method, but space core clusters fluid. You can use tracer, temperature logs, possibly. You can go in, with the Zeeble system is pretty good. Or step down test can give you an idea. Those are a little bit fuzzy, but still, do a step down test. Go drop about 3 rate increments down to stabilize the rate and look at that. That'll give you your perforation efficiency, which with one cluster per one hole per cluster will give you the efficiency.
Okay, the next question here is from Carlos Pineda. Bob, really good presentation, thank you. The question is, as operators confirm increase of production with shorter cluster spacing, even though many are reducing the quantity of holes per cluster, why is it that they are getting increase of production? Does it have to do with the hydraulic fracture reaching more clusters?
Not sure I understand the question.
Carlos, you want to elaborate?
Yeah, Bob. So obviously, that more clusters in one stage. When the clusters closer together, they have seen increase of production.
Right.
But why is it in the past, or we know that still the gases, as we're fracturing, the path of least resistance is where the frac is going to go into which cluster. So why is it that we are increasing production if that's still happening?
Sure, good question. The work that Kyle Hosfite did with Devin with the sealed well bore, I've got a slide in there with his SP paper number, I think shows you why. I mean, if you've got XLE going on, if it's working effectively, you're going to be able to get pretty much equal flow into each cluster. I was surprised and somewhat shocked in the wells. We looked at 197 wells in the Midland Basin, that the average delta P across the perfs from the ones that we used to calibrate the recovery factor was about 1,200 pounds. Using XLE, a lot of them using 4 shots a foot. A lot of them, nobody was using 6, but XLE is not universally used out there. So, I think you've got to use XLE to make that happen. You've got to make sure that you're getting equal flow into all your equal pump rates into each cluster by doing that. So, I mean, it's somewhat random in that respect if you don't. And I think we were getting the numbers, and we got a distribution on our numbers. You can see it. Not every well was 13.7. That was the P50. Some are a little bit higher, some are a little bit lower. You've got some uncertainties. We assume a 330-foot width drainage area or radius drainage area, 660, which is, borne out by a lot of RTA work is in that ballpark, but that's not an exact number. But we're consistent from well to well on our recovery factors on that. But no, if you increase your SRV, if you use XLE and close cluster spacing at the same time, now if you don't use XLE, you can have really random results. I mean, you can end up with everything going into a frac. You can have, I've heard of hitting an existing natural fracture and flying, and with XLE and with Refracs, the same thing. If you hit an existing drain cluster that's been produced before, an old cluster that's been producing for several years, you could put all your frac right there, and that's not good. So you've got to use XLE along with this, and a lot of people aren't. So that may be part of what we're talking about there. I hope I answered your question.
Yes, thank you.
Yes, and I don't know if this is a continuation. I guess, Carlos, you can comment if you need to. Do you know if the production decline timeline has changed for those wells with shorter cluster spacing? Do they decline as quick as the ones with the longer cluster spacing?
I haven't seen any work on that one way or the other. You should get more. You should get higher EURs. I mean, that's a given.
Mm-hmm. Or the closer cluster spacing, right?
Right.
Mm-hmm. Yeah.
Okay, our next question here is from cluster spacing and cluster efficiency, the difference between XLE and diversion.
Well, cluster is just, you have basically an entry point in your casing, for the frac. It's a perforation. Usually it's a series of perforations. Very few people are doing the one shot per cluster right now. I think Liberty's doing it. A few other operators are doing it.
Presentation here. Pay it forward.
But yeah, and the cluster spacing is just how far apart they are, and then the efficiency is how many are taking fluid.
Someone's doing a presentation, or?
Was that the question? Or?
I'm not sure.
Oleg, you have, Atik, you have other things to clarify? Atik, are you there?
Yes, I got it. It's okay.
It's okay?
We good?
Yes, it's okay.
Alex, go ahead with the next
question.
Okay,
our next question is from Carlos Pineda. Regarding hydraulic fracture efficiency, do you have any production data comparing wells where 100% of the clusters were taken the frac versus those that were hydraulic fracture took the path of the least resistance, leaving some clusters with less and others without sand? Do the ones with 100% frac efficiency produce longer?
A lot of the work on that was done by Paul Weddle at Liberty. They did a comparison between the conventional perforating and XLE with cluster efficiency. And I'm pretty sure there was some production data in there as well. I mean, the link between SRV and your EURs is not even a question anymore. I mean, that's like that's a given. I mean, that's not something that really is open for debate. The question is, are you getting better SRVs with higher cluster efficiency? And again, I'd say, yeah, I mean, you have to be. I mean, you're putting more fluid, you're leaving fewer gaps. I mean, look at that example from the Eagle Ford. I mean, with 50-foot cluster spacing, you were getting, 85% of your rock wasn't even being drained. I mean, so your SRV was only 15% of the rock. So, you're definitely going to get better production out of your closer cluster spacing with higher. That's pretty basic, isn't it?
Yeah, and I assume that. Yeah, thank you for the answer, Bob. And so my mind goes into also the single point entry, fracking with sleeves, where at 100% efficiency and therefore producing. Leaving cost aside, I was also speaking with an operator friend for the Northeast, where they did a single point entry, but with plug and perf, where they did one cluster at a time, and that well has been incredible in production. So,
well, it depends on what you're comparing it to. I mean, if you have wells around it that used XLE, I would suggest you probably don't, because it's a lot of people aren't using XLE. And like I said, with the study we had 197 wells we looked at, none of them are using XLE. I mean, and it's remarkable that we got results as consistent as we did, because without XLE, statistically from Paul Weddle's paper, you're looking at about a 50 to 60%, I think it was 59%, I think, average cluster efficiency without XLE. And with XLE, you're looking at 85 to 90%. So, I mean, your results could be significantly different. Now, going with a single point entry point, that's going to guarantee everything gets treated. But the problem there is, why do that when you look at Kyle Hosfite's paper you just presented at the HFT? If you're getting equal flow into all your clusters, there's no reason to go to a single entry point. I mean, it's, now if you're not, yeah. I mean, if you're for some reason you don't want to use XLE and you don't want to have equal entry flow going into your early clusters, and you want to take the risk of, runaway fracs and all your fracs going into one depleted cluster, then yeah, single entry point is a way to get around that. But I don't think it's the least. I mean, you said ignoring the cost that's a big statement right now, because
yes,
prices being down where they are. I don't see any reason. I apologize to my buddies at NCS because I've got a lot of good friends over there. But I mean, in a lot of cases like this, I'm not sure that's something you got to look at real hard. I mean, I see that sometimes for matrix type reservoirs being very good. If you're not really trying to do it, because organic shales and matrix reservoirs are completely different. For instance, like your Joe Mill formation, your Bone Springs formation, they're actual real reservoirs. Even the Bakken, for that matter, the Bakken's got about 0.02 millidarcies. I mean, it's not an nanodarcy organic shale. Everything I talked about here is for nanodarcy organic shales. I'm not talking about trying to optimize a Bone Springs completion or a Joe Mill completion, because in those cases, the single entry point makes a lot of sense, I think, because you don't really need the complexity. You're not really trying to create permeability. It depends on whether you're trying to create permeability or whether you're trying to extend the effective wellbore radius where the existing permeability can go in. If you're trying to extend the wellbore radius, which is a conventional fracturing physics, then the single entry point makes a lot of sense. But if you're trying to disrupt the rock, and I think you really need the stress shadowing to help in the organic shales, because you're basically not draining 100% SRV to start with, but with your cluster shadowing and cluster stress shadowing, intercluster stress shadowing, you're getting much more complex fracs. I mean, you're going to increase the complexity. If your maximum stress direction is coming from about 5 different angles, that frac's going to look a lot different than a planar fracture, which is what you're going to get with a single entry point. Because a single entry point will give you a planar fracture, not a complex fracture. And but for matrix reservoirs, that's fine. That's all you need. I mean, a lot of these are kind of scary to me. A lot of these matrix reservoir fracs, you're using organic shale spacings on them, and going like, I've got a 0.04 millidarcy reservoir in the Joe Mill, and you're you're putting your clusters 12 feet apart. Wait a minute, that's kind of like, spindle top kind of comes to mind. You're right, you're draining the same rock over and over again. So that's where the single entry point, I think, makes a lot more sense in those formations.
Okay, our next question here is from Jeffrey. Do you / operators have good production curves for pre and post refrac candidates?
Probably the best source there would be Devon has done a big program in the Eagle Ford. Also, Conoco has done a big program in the Eagle Ford, and I think Devon's reporting a 40% increase in their EURs on the refrac wells, and Devon was or Conoco 60%, I believe. And that's been come out in the last year or so. So yeah, there's a lot of data out there. And again, they've done what the difference there is that they consistently reline their wells. They mechanically isolate every well and use best practices. So they're and the results are very good. It's Conoco said they had something like 600 refrac candidates they were looking at. One of the presentations they made last year at Doug Eagle. Yeah, there's a lot of data out there to show that it works.
Okay, our next question here is from Mamdou. For refract efficiency, would you use micro seismic for monitoring with fiber optics?
I haven't really seen that much. I don't think you've got the resolution on that. You might get some idea of your producing height from that, although I'm not really even sure that's that you're seeing what you're seeing. And even fiber optics right now, I mean, a lot of these, I mean, we've kind of they've already kind of done the work. I mean, the companies that have done the fiber optics already have gone out there and showed you that it's going to XLE and basically helped establish best practices. You can verify that again if you want, but a lot of this is just basic physics. The stuff with the XLE and the stuff that Kyle Husfight, that's basic physics. It's not, it should work just from a theoretical point of view, and he's proven it works. So, I mean, you have to keep reproving that. I mean, I'm not sure that's necessary, particularly in today's pricing environment. I mean, there's not a lot of spare money floating around for science projects out there. It's people are pretty much hunkering down and getting it done at the lowest possible cost. And you start adding all these things like microseismic and even fiber for that matter. It's good. They're good techniques, but I think they're better to use when you have a little better price cushion, because right now everybody's just kind of trying to survive out there. It's if you already know something works, and I would recommend you just believe that it works and not try to reinvent the wheel. At this point, I mean, a year ago I wouldn't have said that. as everybody is more than well aware, unfortunately.
Okay, our final question here comes from Herman Vaca. Can you reiterate on bookable reserves from Refracs, i.e., is it catching on or why not?
Good question, Herman. Good question. The first work on that, and it was off my radar screen until Samantha presented that paper back in 2015 at one of these little Refrac conferences. And to me, at the time, it sounded like a great idea, but when I looked around at what people were doing, remember 2015 was still the diverter age. I mean, people were still trying to figure out how many feet of lateral you can divert at one time. I think the Core Lab presentation and ProTechnics at the annual meeting in 2015 said something like 2,000 feet is your number that you want to look at, no more than 2,000 feet on the lateral. But even then, that's not really, I mean, that was not good. But I think what's made the difference is since 2017, which was, I think, was a tipping point for expandable, or not just expandables, but just mechanical isolation, period, was really not the key method. Before 2017, the majority of the refracs were done with the diverter. Post 2017, the majority of the refracs, and 100% of the successful refracs, the majority of the refracs were done with mechanical liners. And I think in order to meet the requirements that Samantha put out, and this is not just Denham Capital. I talked to Ryder Scott about this. I've talked to another reserve engineer group about it. And they all say, yeah, as far as PRMS goes, which is the SP, guidelines, which y'all are familiar with, I'm sure. Yeah, there's no reason why it shouldn't work. There's absolutely no reason why, if you meet those requirements. The problem is people aren't doing, I mean, how many people do you know are doing 6 refracs? I mean, Conoco doing it, Devon's doing it, and those are the 2 companies I talked to see if they were doing it, and I haven't heard back from Devon yet. But Conoco got back to me and said they hadn't really looked at it yet, but it's brand new. I mean, it's not something that a couple of years ago you couldn't do it. So it's something that really hasn't got people's attention yet. But I think when people start seeing this, and I think it's only going to take one operator to do it to open the floodgates. And if it does, it's going to be nuts out there. I mean, because there's absolutely no reason why it wouldn't work. I mean, you've got the reserves behind pipe. If you consistently show that I can take a well with a 5% recovery factor and turn it into a 14% recovery factor well, and with no surprises, and consistently and economically at low cost, which is all what we're focusing on here too as well, then there's zero reason it shouldn't work. Now, why it hasn't worked, I mein, I've got hundreds of cases of that in my past trying to develop new technology. Why people aren't using stuff? I mean, I think it's an education process, and I think once people get aware of what the benefits are, the ROI on that is just off the charts. I mean, what, 7.5 to 1, something like that. $20 million refrac investment will get you $160 million worth of present value. That's off the charts. But it's real, because you can, if you show you can go to a well with certain characteristics. Now you're gonna have to, one of the challenges is gonna be, getting the reserve people to buy into your petrophysics, which may or may not work. You're probably gonna have to value the PV20 not on the way I did it. I valued it on the petrophysics using the recovery factors, where you're probably gonna have to estimate your PV20 off of what's, what the wells actually did, are going to be where your PV20 comes from. Now, it should be what we predict. I mean, there's no reason, because again, that's also basic physics. But that's the assumption I made. So that number may be off. Say for instance, you have a number of fracs that weren't completely optimized for whatever reason. That you may get a lower number than that. But it's going to be a whole lot. You're going to get money for nothing either way, because you've got reserves behind pipe, and once you show that you can consistently get them out there, which in the past you weren't able to do, I think it's going to be big. I mean, it should be. I mean, is it going to be? I mean, nothing surprises me in this business. It may never take off, but it should. I mean, it really should. But good question. Very good question.
Are there other questions, Alex?
Sorry, no, that was the final question that we had.
Okay. Actually, Bob, I have a few other questions, but I'm not going to do it now. If you go to our network section, maybe I can ask you. I can be in the same breakout room as you are. Then at that time, I can ask you those questions. Okay. And now, Alex, Francisco or Carlos, are we going to take a picture of all of us together with 2 speakers right now before we go to the breakout room?
Francisco has been taking pictures of the whole group, and I took a picture of Jorge Jorge's and Bob's main slide with their picture in it. So
Okay.
that's been taken care of.
Okay, great. Thanks a lot. I appreciate it. Now, if there are no other questions, and if both of our speakers are willing to get with us to the networking room, I think we have 23 participants at the moment. And Griffin, you take it over, please, and you reclaim the host status.
The one thing, I'm sorry, Salim, just to have a good one here. Can everybody turn on their videos? And yeah, we'll take a picture of everybody with their videos on.
Make sure you're smiling and you're in the middle of the monitor. Make sure that you're not hiding away or just your eyes, that you don't look like this. Doesn't look good. Okay, so when everybody turns on, then I'll take the picture.
I need a permission to open my video.
Okay. I'm doing that.
Who you need the permission from?
I don't know. I just tried and it says permission needed.
From?
Carlos will do that.
Who is the host now?
It's done.
It's done? Okay. Great. So do you have your picture now, video?
I need Carlos' picture. I need Carlos' video, Griffin's video, Herman's video.
There you
now
are.
they're showing up. Oh, okay. So,
Alex, you will be collecting all the pictures and collaging it and posting it onto LinkedIn, right? This time?
Yes.
Okay, thank you. And if you need any help, Chris Mayo is going to help you.
okay, so the only one, well, I guess this is it. We have 1, 2, 3, 4 that they don't want to show up in the picture, but that's fine.
Make sure you don't have lettuce in your teeth.
8. Okay, let me take one more. And
Salim, look at the camera.
Yeah, sorry. Yeah.
Ready?
Perfecto mundo. I got everybody now. And thank you very much.
Thanks, Francisco.
Now we go into the breakout rooms as you were planning.
Yes, please. Okay, go ahead, Griffin. Take care of it.
All right, thanks. So thanks for Jorge and Bob for excellent presentations. Jorge, I have some exposure to perforations from working as a reservoir engineer, but just like any topic, when you get closer to it, you see there are all kinds of details and challenges to overcome. Thanks for bringing us to the next level of understanding perforation. Bob, when you said there were more refrac conferences than refracs in the field, I was laughing too, but you gave us a wealth of practical information from your experience, so thank you.
Thank you.
So next we'll have the networking breakout rooms, and I hope you like networking because it's important no matter whether you have a job, you're looking for a job, or what your situation is. You can share information, you can get information. It's so valuable. So I hope everyone will stay for the networking. So I'll tell you more details on that, how that works in just a moment. We have a happy hour coming up next week on Thursday, on June 11th at 5 p.m. So I'll be sending in the Eventbrite invitation for those. Hope you can join us. So based on the number of people we have on the call, I've split us into 3 rooms, 3 breakout rooms. First one will be with Jorge on the perforation topic. The second one will be with Bob on Refracs topic. And the third is general networking. And I've pre-assigned everyone according to kind of their interests shown in the Q&A. So maybe next time, if you want to be for sure in one room from the beginning, write in a question. But this time, if you want to change, you can just say so, or you can send me a note in the chat window, and I'll be glad to change the breakout room that you're in. So in a moment, I'll click to open the breakout rooms. You'll see a message that says you've been invited. And you can either join now or later. If you're not ready to, you need to take a little break or something, or if you need to go. And when you tap to join it, your current screen will go away and it'll recreate you in the breakout room in a few seconds. And there you'll be able to talk with everybody. I hope you take advantage and make the most of that time. And thanks for attending.
Great.
Any questions about how this will work?
Sounds good.
All right.